Hello there, and welcome to The Tired Thinker, where ideas slow down and thought takes its time. Tonight's quiet reflection is about something every programmer eventually faces: reality shifts. They creep in when deadlines move, when requirements change overnight, when code that once felt solid starts to unravel under new demands. These shifts don't care about your clean abstractions or elegant designs. They bend your careful plans until they break. You may notice them in small ways. A feature that worked yesterday fails today, or a decision that seemed smart last month now feels like a trap. Or they may arrive all at once: a system collapsing under unexpected scale, an API changing without warning, or business needs overriding all sense of structure. The truth is, reality always has the final say. And in programming, those shifts will test not just your code, but your patience, your judgment, and your ability to adapt. Before we begin, I'd love to know, where are you tuning in from, and what time is it right now, in your corner of the world? It's strange, isn't it? A talk about broken code, and yet here we are, scattered everywhere, quietly linked by the same challenges. If you find this kind of slow thinking calming, or if you're just here to give your mind a softer place to rest after a long day of debugging, I'd be grateful if you gave the video a like, or gently subscribed. It helps this tired little channel reach others who might need a quiet moment of reflection too. Now, let's begin. When you begin your journey as a programmer, it is easy to think the main task is writing code. You imagine long hours spent typing new features, building fresh systems, and adding functionality. The reality feels different once you spend time in real projects. You discover that most of your hours go into reading code, not writing it. You read to understand what others wrote before you. You read to debug issues and to figure out how the system behaves. You read your own code from last week or last year, trying to recall why you made certain decisions. Because of this, writing code for clarity becomes more valuable than writing code fast. Imagine walking into a large code base that has been around for 5 years. Dozens of developers have contributed, and thousands of files exist. A bug report lands on your desk. The feature worked fine last month, but now fails under certain conditions. You open the relevant part of the system and begin tracing the logic. The challenge is not that the code is broken in an obvious way. The challenge is that you must understand how it was written. If the code is clear, with descriptive variable names and straightforward logic, you make progress quickly. If it is dense, filled with clever one-liners or hidden shortcuts, every step becomes slower. Reading becomes the real task, and how well the code was written decides how painful the work will be. A good way to see this is through the difference between a short, clever trick and a longer, clear solution. Suppose you need to filter out even numbers from a list. In some languages, you might write a compact expression that looks like a puzzle to anyone new to the syntax. It works, but the next developer must stop, recall the rules, and test it in their head. On the other hand, you could write a simple loop that checks each number and only keeps the ones that match. It may take 3 more lines, but the intent is obvious. 6 months later, when you return to the same function, you will thank yourself for being clear instead of clever. The computer does not care about your elegance. It cares about correct instructions. Humans, however, must maintain the system, and humans benefit most from clarity. Reading also dominates time because of debugging. When you debug, you search through layers of code to identify the root cause of an issue. Each layer requires careful reading. You ask yourself questions: who changed this variable? When was it updated? And why did it behave differently in production than in testing? The time you spend debugging depends heavily on how understandable the code is. Comments that explain intent reduce confusion. Consistent formatting prevents you from getting lost in a sea of braces and parentheses. Clear separation of functions reduces the mental load of tracing logic. Each of these practices saves you hours in the long run. Consider another scenario, where you join a team and inherit a service written 3 years ago. The developer who wrote it has moved on. No one remembers the original reasoning behind certain design choices. You must extend the service to support a new requirement. If the code is easy to read, with functions named after what they do and variables named after what they hold, the task feels possible. If instead the service hides meaning behind vague names like temp or object, you are left guessing. You may even break the system by misunderstanding how it works. This is why writing clear code is an act of respect for future developers, including yourself. Clarity in code comes from simple habits. Use names that describe purpose rather than form. A variable named userBalance tells you what it represents, while one named x1 forces you to look elsewhere for meaning. Keep functions focused on a single responsibility. A function that both updates a database and formats a message mixes tasks and confuses the reader. Write comments only where they explain intent, not to repeat what the code already states. If you find yourself writing a comment that says increment counter, perhaps the function name should instead be increment counter. Clarity often means reducing the need for comments by letting the code speak for itself. One might argue that writing fast is the real skill, since deadlines often push teams to deliver quickly, yet the cost of unclear code shows itself later. Every shortcut that sacrifices readability becomes a tax on future maintenance. Bugs take longer to fix, new features become harder to add, and onboarding new team members slows down. In the end, the time saved during the initial writing is lost many times over in later reading. Teams that invest in clear code build systems that last, while teams that favor speed alone often drown in technical debt. Think about how you learn a new programming language. You rarely start by writing complex systems. Instead, you read examples, tutorials, and documentation. Reading shapes your understanding of the language. The same is true in professional code bases. To understand how a system works, you read what others wrote before you. When code is readable, it becomes a learning tool. When it is not, it becomes a barrier that slows both understanding and growth. Another way to see the value of readability is in code reviews. When you submit code for review, your peers read it to ensure it meets the team's standards. The easier it is for them to read, the faster they can approve it. If they struggle to follow your logic, they must ask questions, suggest changes, or even reject the submission. Clear code saves time not just for you but for everyone who interacts with it. Reviews go smoother, bugs slip through less often, and the team develops a shared sense of trust. Clarity also helps when tools fail you. Linters, formatters, and static analyzers can point out problems, but they cannot replace human understanding. A piece of code may pass all automated checks and still confuse every person who reads it. The true measure of good code is not whether it compiles or passes tests, but whether someone else can understand it without struggle. Writing for clarity ensures that your code remains usable beyond the moment it was created. The idea that code is read more than written challenges the romantic notion of programming as pure creation. It shows programming is closer to communication. You communicate with your team, with your future self, and with anyone who inherits your work. Each line you write is a message. The clearer that message, the easier it is for others to continue the story. And since reading always outweighs writing in time spent, the value of clarity becomes impossible to ignore. When you begin programming, there is a strong temptation to write clever code. You learn new tricks, discover shortcuts, and enjoy compressing many operations into a single line. It feels satisfying to write something that looks elegant and compact. You may even feel proud when others notice how little code you use to solve a problem. But cleverness often creates more harm than good. Code that is short and cryptic today will confuse both you and your teammates tomorrow. Simple code, even if it looks longer, is easier to maintain, easier to debug, and easier to scale as a system grows. Imagine a function that reverses a string. A clever developer might use an obscure built-in function with a chain of modifiers that looks like a puzzle. The code might fit on one line and appear brilliant to those who recognize the trick. Yet when someone new to the team encounters it, they stop and ask what it does. They copy the line into a console to test it, because the meaning is not obvious at first glance. The time saved when writing the one-liner is lost many times over when future developers try to read it. Now imagine a different version written in a few lines, loop through the string, build the result in reverse and return it. Anyone reading this version knows instantly what happens. There is no guesswork and no hidden logic. The longer version is the better one because it is simple. Clever code often hides intent. The purpose of a function is not only to run correctly, but also to tell the reader what problem it solves. A series of chained operators, nested ternary expressions, or deeply compressed syntax may solve the task, but it hides the thought process. When you or another developer revisit the code months later, you must decode it like a riddle. Simple code does the opposite. It makes the intent clear. It may take more lines, but each step shows the reader the reasoning. This clarity builds trust in the system, since developers can read it without guessing. Think about debugging. When a bug appears, the first job is to trace through the code to see what happened. Clever code increases the mental burden of that process. Suppose you encounter a bug in a function that calculates discounts for a shopping cart. If the function is filled with dense logic compressed into a few expressions, you must unravel it line by line, often adding print statements to see what each part does. If the same function is written with simple branching and clear variable names, debugging is easier. You can follow the logic without extra effort. Each conditional statement or loop tells you exactly what is happening. In stressful situations where a bug must be fixed quickly, simple code is your ally. Simplicity also helps in team environments. Software is rarely written by one person working alone. Most projects involve teams where people come and go. New developers must read existing code to get up to speed. Clever code creates barriers. It signals that the author valued personal expression over team understanding. This creates frustration and slows progress. Simple code, on the other hand, makes collaboration smooth. A new teammate can read it and contribute without long explanations. The shared understanding grows because the code is approachable. Consider a scenario where two developers take different approaches to the same problem. One writes a function that calculates the total price of an order with discounts and taxes. They use a long one-liner with chained operators, inlined calculations, and implicit type conversions. The code works but looks dense. Another developer writes the same function in multiple lines. They break the logic into steps, calculate subtotal, apply discounts, calculate tax, then add shipping. Each step has a variable that describes the result. Reading the second function feels like reading instructions. Even someone new to the project can understand it. When the business rules change, the second function is easy to modify. The first one requires careful analysis to avoid breaking hidden logic. This shows why simple code scales better. Frameworks and libraries often encourage clever shortcuts. Many provide features that allow developers to write in compact styles, but these features should be used with caution. For example, a database query written with heavy use of chained methods may look neat in one line, but when performance issues arise, tracing that query is difficult. Writing the query in a more verbose style, with clear conditions and explicit joins, makes it easier to optimize later. Cleverness often hides costs, while simplicity exposes them. Another way to see the value of simple code is in code reviews. During a review, peers must read and understand your changes. Clever code slows the process. Reviewers may spend time asking for explanations instead of assessing correctness. This delays approval and increases frustration. Simple code, by contrast, invites quick understanding. Reviewers can focus on whether the logic matches the requirement, not on deciphering syntax. This leads to faster reviews and fewer mistakes slipping through. Even outside of teams, your future self benefits from simple code. Imagine returning to a personal project you abandoned a year ago. You open a file and see clever one-liners that you once felt proud of. The problem is that you no longer remember the trick. You must relearn what you once knew, wasting time. If instead the code was written in simple, direct steps, you would pick it up immediately. In this way, writing simple code is a form of kindness to yourself. Some developers argue that cleverness saves space and reduces redundancy. They believe that shorter code is always better. This view ignores the real cost of complexity. The cost is not the number of lines, but the time it takes to understand them. 100 clear lines may be easier to work with than 10 clever ones. Code is not written for compilers alone. It is written for humans who must read it, extend it, and fix it. Computers can run any valid syntax, but humans need clarity. There are times when clever code may seem appropriate, such as in algorithm competitions or when writing very low-level performance-critical code. In those cases, every microsecond or byte counts. But most real-world programming does not live in that space. Most systems value maintainability over micro-optimizations. The extra milliseconds saved by a clever trick are nothing compared to the hours lost when debugging unreadable code. Choosing simplicity is a better long-term strategy. Simplicity does not mean dumbing down. It means expressing the logic in a way that is easy to follow. It means structuring code so that each part does one job and does it clearly. It means resisting the urge to show off language tricks and instead focusing on communication. The goal is to write code that another developer can understand without effort. This principle holds across languages and frameworks, across small scripts and large systems. Simple code scales because it invites people in, while clever code pushes them away. When you first learn programming, time feels simple. You write a function, call it, and expect the steps to run in order. One thing happens, then the next, and you can trace the flow from start to finish without confusion. This neat model works when your program handles one task at a time, but real systems rarely live in that clean world. The moment you introduce concurrency, asynchronous tasks, or shared resources, your neat step-by-step logic shatters. Programming becomes less about writing a sequence of steps and more about orchestrating chaos that you cannot fully control. Imagine you are building a web server. A user sends a request, the server processes it, and then it responds. If only one user connects at a time, the logic feels straightforward. But what happens when hundreds or thousands of users connect at once? Each request must be processed, and the server cannot wait to finish one before starting the next. It must juggle many tasks at the same time. Now your code does not run in a single line of order. It runs across threads, processes, or event loops. Each piece competes for CPU time, memory, and access to shared data. The flow you once traced in a straight line now looks like a tangled web. Concurrency introduces race conditions. A race condition occurs when two or more parts of the program try to access or modify the same resource at the same time, and the outcome depends on the order of operations. Suppose you have a banking application where two people try to withdraw money from the same account. If both requests read the balance before either updates it, they may both think there is enough money. They withdraw simultaneously, and the account ends up overdrawn. This bug does not appear in every run. Sometimes one request finishes before the other starts, and everything works fine. Other times they overlap and chaos unfolds. Because the order of events depends on timing, you cannot predict the result by looking at the code alone. Asynchronous programming adds another layer. In many modern systems, tasks wait for external events, such as network responses or file reads. Instead of blocking until the task finishes, the program moves on and comes back when the result is ready. This improves efficiency, but it also means your code does not run in the order you wrote it. For example, imagine a function that fetches data from two different servers. You write code to start both requests and then process the results. You may assume server A will respond first, because it usually does. But one day, server B responds faster, and the results arrive in the opposite order. If your code assumes a specific sequence, it fails. The truth is, you cannot control when each event happens. The program must handle results in whatever order they arrive. Consider the case of updating a shared file. Two different background tasks attempt to write changes at the same time. One task adds a record, while the other deletes one. If the writes overlap, the file may become corrupted. To avoid this, you need locks or transaction systems to enforce order, but locks themselves bring new problems. If two tasks wait on each other's locks, they may both stop and never continue. A situation called deadlock. Preventing deadlocks requires careful planning of how resources are requested and released. This again shows that time is not under your control. You can only put rules in place to manage the chaos. Even small examples make the point clear. Suppose you build a chat application with notifications. A user sends a message, and the server saves it to the database while also sending a push notification. Which happens first? If the notification goes out before the database write finishes, the receiver may click on it and find nothing new in the chat. If the database write finishes first, everything looks fine. The system must account for both possibilities. You cannot guarantee that one will always happen before the other, because network delays, server load, and many other factors influence the timing. In distributed systems, the problem grows larger. Different servers run in different locations, often across the globe. Each one keeps its own clock, and those clocks may not agree. A log entry written on one server at 10 o'clock may actually occur after an entry on another server labeled 10:01, because of clock drift. When you try to trace events across systems, the timeline can look inconsistent. Engineers build synchronization protocols like NTP or logical clocks to manage this, but even then, perfect agreement is impossible. You must accept that time in distributed systems is approximate. This lack of control affects testing as well. Bugs related to timing are some of the hardest to reproduce. You may run the same test 100 times and see it pass, only for it to fail once under heavy load. The failure depends on tiny variations in execution order that you cannot force at will. Debugging these issues requires logs, tracing tools, and sometimes even simulated environments where you inject delays to mimic real-world timing. Writing tests for concurrent code is never as simple as writing tests for sequential code. Developers use patterns and tools to manage the chaos. Locks, semaphores, message queues, and event loops help coordinate tasks, but each tool comes with trade-offs. Locks prevent race conditions but can cause deadlocks. Message queues ensure order but add latency. Event loops simplify concurrency but shift complexity into callbacks and state management. None of these eliminate the problem of time. They only shape how you deal with it. You design systems not to control time, but to tolerate uncertainty about it. Think about user experience. Suppose you design a mobile app that loads data when it opens. If you assume the data arrives instantly, you will frustrate users when the network is slow. The correct approach is to accept that you cannot control when the data arrives and design for it. You show a loading state, allow users to retry, and ensure the app does not freeze. By acknowledging that you do not control time, you create software that feels more reliable to users even when the world is unpredictable. Your mindset as a programmer must shift from expecting order to preparing for disorder. Instead of asking what happens first, you ask what happens if these two things happen at the same time. Instead of trusting that a task will finish quickly, you design for the case where it takes longer than expected. Instead of assuming a resource is available, you prepare for the case where it is locked or busy. This mindset does not eliminate chaos, but it helps you build systems that function within it. Programming starts as an exercise in logic, but real systems remind you that logic runs on time, and time cannot be controlled. CPUs switch between tasks, networks delay packets, disks take longer to spin, and clocks disagree across servers. Each of these factors breaks the illusion of neat, step-by-step execution. You learn to live with this reality by writing code that expects the unexpected. In this way, programming becomes less about commanding time, and more about working around its unpredictability. When you first learn to program, most exercises focus on logic and math. You write functions to sort numbers, calculate factorials, or find prime numbers. These problems have clear steps and clear answers. They teach you how to think like a programmer, but they do not show you the real weight of software development. In practice, the hardest part is not the math or the algorithms, it is the state. State is the record of what the system knows at a given moment. It includes the values in memory, the rows in a database, the flags in a session, and the files on disk. Managing state across components, databases, and services creates more complexity than most mathematical challenges ever will. Imagine a simple to-do list app. At first, it feels straightforward. You let users add tasks, mark them as done, and delete them. If you store everything in a single file and only one person uses it, the logic is easy. The state is small and predictable, but as soon as you allow multiple users, the state begins to grow. Each user has their own tasks. The database must separate them. What if two people share a task list? Now you need rules about who can change what. What happens if one person marks a task as done, while another deletes it at the same time? These are not math problems. They are state problems, and they are much harder to reason about. Bugs often hide in state transitions. Suppose you build an online store. A customer places an order. At that moment, several parts of the system must update state. The database records the order. The inventory system reduces stock. The payment service charges the card, and the notification service sends an email. If any one of these fails, the system can end up in an inconsistent state. Maybe the customer gets charged, but the order never appears in the database. Maybe the email goes out, but the payment fails. Debugging these situations means asking the question, who changed what, and when did it happen? You are not solving an equation, but trying to piece together the history of events across different systems. State also explains why caching is difficult. To make systems faster, developers often store temporary copies of data in memory, but caches create new layers of state that must stay consistent with the source of truth. Imagine a news site that caches articles for speed. A journalist updates a story, but the cache still serves the old version for several minutes. Readers see outdated content, and confusion spreads. The code to fetch and display the article may be simple, but the challenge lies in keeping the cache and the database in sync. State drift becomes the problem, not logic. Concurrency makes state even harder to manage. When multiple threads or processes run at the same time, they often share state. Two threads might update the same counter. If both read the old value before either writes the new one, the final result is wrong. This race condition happens because state was not protected. Locks, semaphores, or atomic operations can prevent this, but they introduce their own complexity. Forget one lock and the bug reappears. Add too many locks and the system deadlocks. These are problems that arise not from difficult math, but from the difficulty of keeping track of state. Distributed systems multiply this challenge. Think of a social network with servers across the world. A user posts a message in London, but another user in New York expects to see it right away. The post must travel across servers, databases, and caches. If replication lags or a node crashes, different users may see different versions of the truth. Engineers call this eventual consistency. It means the state will align eventually, but not always instantly. Debugging such issues often feels like detective work. You look at logs from different servers, compare timestamps, and try to reconstruct how the state diverged. The bug is not in the syntax of the code, but in the movement and timing of state across a wide system. Even in smaller systems, state trips developers. A common bug in web applications is the stale session. A user logs out, but their session token remains valid somewhere in memory or cache. They still have access when they should not. The code to log out is only a few lines, but the state involved touches cookies, server memory, and databases. Miss one step and the bug persists. Again, the problem is not complex algorithms. It is the difficulty of making sure state changes everywhere they should. Consider the life of a database transaction. When you wrap a set of operations in a transaction, you ask the database to treat them as one atomic action. If all succeed, the state changes. If one fails, none should. But in real life, failures happen mid-transaction. A server may crash, a network may drop, or a timeout may occur. The database must then decide how to roll back. If it fails to roll back correctly, the system ends up with half-applied state. This is one of the hardest kinds of bugs to track, because it does not happen every time. It happens only when certain failures align in a certain order. When you investigate, you ask the same question: who changed what, and when? State also explains why testing can feel incomplete. You can write tests for logic, but state adds hidden variables. Suppose you test a function that calculates discounts. It passes in isolation, but in production, the function reads user data from a session, product data from a cache, and price data from a database. If any of these sources contain unexpected state, the function behaves differently. The test never covered that case. Bugs slip through because the state at runtime differs from the state in tests. Version control itself is an attempt to manage state. A Git repository does not just hold code, it holds history. Each commit records what changed and when. Without it, collaboration would collapse. Developers would overwrite each other's work, and no one would know which version was correct. Git works because it tracks state carefully, yet even here, conflicts occur. When two people edit the same file, Git cannot always merge them cleanly. Humans must step in to decide the correct state. The difficulty lies not in the math of merging, but in deciding which state to keep. Even user interfaces struggle with state. Think about a simple form on a website. A user enters text, clicks submit, and waits for a response. If the network fails, should the form clear? or keep the text? If the server responds with an error, should the page refresh or highlight the problem? Each of these choices reflects how you manage state in the interface. Poor handling leads to frustration, as users lose work or see inconsistent screens. Good handling makes the system feel reliable. The more you build systems, the more you see that state drives complexity. Variables, caches, sessions, databases, distributed services, and even user interfaces all hold state. Each one changes over time. Each one interacts with others. The hardest bugs appear when state drifts, when updates conflict, or when history becomes unclear. Managing state means tracking not just values but their origins and timing. It is this challenge, more than the math of algorithms, that defines the real difficulty of programming. When you learn programming, you quickly encounter abstractions. An abstraction is a layer that hides detail so you can focus on a higher level idea. Frameworks, libraries, and APIs exist to make work easier by covering up the complexity underneath. Instead of writing raw SQL queries, you use an ORM to handle the database. Instead of writing socket code, you use an HTTP library. Instead of building everything from scratch, you rely on a framework that sets patterns for routing, authentication, and rendering. These abstractions save time, but they all share one truth: every abstraction leaks. The details you thought you could ignore eventually surface, and you must understand what lies beneath. Consider an ORM, or Object Relational Mapper. Its purpose is to let you interact with a database as if it were just objects in your programming language. Instead of writing select and join statements, you call methods and chain filters. At first, this feels magical. You can fetch data with a few lines of code, but as soon as the queries become complex, the leaks appear. Maybe the ORM generates an inefficient query that performs poorly on large tables. Maybe it fetches too much data into memory because you did not specify the right filter. You thought you could forget about SQL, but now you must learn it to diagnose the problem. The abstraction has leaked, exposing the database layer you hope to avoid. Frameworks create similar moments. They provide structure and conventions so you do not need to reinvent the wheel. A web framework might handle routing, templates, middleware, and background jobs. At first you enjoy the simplicity, but when you want behavior that falls outside the common case, you hit the edges. Suddenly you need to understand the internals of the routing system or the life cycle of a request. You realize the framework made decisions on your behalf, and you must now dig through documentation or even the source code to change them. The abstraction promised freedom from detail, but in reality it only delayed your encounter with it. APIs also illustrate this idea. Imagine you use a cloud storage API to save files. The documentation says you can upload and download with simple method calls. In testing it works fine, but in production a large file upload fails halfway. The API returns an error code you have not seen before. To fix it, you must learn about chunked uploads, retry strategies, and network timeouts. The simple upload method was only a thin cover over a complex distributed system. The leak shows itself when the system behaves in a way the abstraction does not fully explain. Even programming languages themselves are abstractions over hardware. You might write in Python or JavaScript without thinking about memory, registers, or threads. The interpreter or runtime handles that for you. But when your program slows down or crashes, you discover that the garbage collector paused at the wrong time, or that memory usage exploded because of object references. At that moment, the abstraction of the high-level language leaks. You must learn about memory allocation, garbage collection strategies, or event loop mechanics. The details matter again, even though the language tried to hide them. These leaks are not flaws but facts. Abstractions cannot cover every possible scenario without cost. If an abstraction hid all details perfectly, it would have to include the full complexity of the system, and then it would no longer be an abstraction. By definition, it simplifies some aspects while ignoring others. The ignored details return when you push the system into less common situations. That is when the hidden complexity leaks into view. Take performance as an example. Many abstractions are designed for ease of use, not efficiency. A simple method call may hide a network round trip, a database join, or a heavy computation. As long as the workload is small, this goes unnoticed. But as soon as the system scales, the performance costs surface. Developers must then peel back the abstraction to see what actually happens underneath. An ORM may hide the database, but a slow query forces you to learn indexes and execution plans. A framework may hide threading, but poor concurrency forces you to learn how the scheduler works. The leak reveals itself in performance problems. Debugging also reveals leaks. When an error message comes from deep inside a library or framework, you cannot fix it by staying at the high level. You must dive down into the stack, sometimes into layers you never touched directly. Suppose your application throws a serialization error while saving data. The top-level code only called save. The error, however, comes from the database driver that cannot convert a certain data type. To resolve it, you must learn how the driver maps language types to database types. The abstraction leaked its internal rules because your case did not fit neatly within them. Scenarios in distributed systems often highlight this principle. Cloud platforms let you create services with a few clicks or API calls. They advertise simplicity, but underneath are clusters of machines, load balancers, and replication strategies. When everything works, you do not need to care. But if a service becomes inconsistent across regions or a node fails, you must understand replication lag, quorum, and failover. The API call to create instance hid a large machinery. The leak shows when the system breaks in ways the abstraction cannot explain at its level. A practical example appears when developers use promises or async ledger weight in JavaScript. At first, async makes code easier to read compared to nested callbacks, but when a promise rejection is not caught, it bubbles up and may crash the process. The abstraction promised simplicity in handling asynchronous work, yet the reality of error propagation leaks through. Developers must understand the event loop, microtasks, and stack unwinding to diagnose why certain errors vanish or crash unexpectedly. Even tools built for developers leak. Version control systems like Git try to make branching and merging easier with commands like checkout and merge. Many tutorials treat these as simple steps. But when you hit a merge conflict, you meet the internals of how Git stores commits, trees, and blobs. The system that once felt simple now requires an understanding of its underlying model. The abstraction leaked at the point where the high-level operation could not cover all scenarios. Understanding that every abstraction leaks changes how you approach software. You still use abstractions because they save time and reduce boilerplate, but you also prepare for the moment they fail. You accept that you must peek under the hood when things go wrong. You learn the basics of the layers below, even if you do not work with them daily. A developer who relies only on the surface layer will be stuck when it leaks. A developer who has seen the internals can dive in and solve the problem. This principle explains why strong engineers learn across layers. A web developer who understands both HTTP and TCP can troubleshoot when requests stall. A back-end engineer who knows ESQL execution plans can fix queries when the ORM generates inefficient ones. A mobile developer who knows memory management can resolve issues when the garbage collector creates pauses. These skills allow you to cross the boundary when the abstraction leaks, which it always will at some point. Abstractions make systems usable, but they do not erase complexity. They shift it, sometimes delaying it, sometimes hiding it until it surfaces in an unexpected place. Frameworks, ORMs, APIs, languages, and tools all promise simplicity, but each one eventually shows its seams. When that happens, you must dig deeper and deal with the reality underneath. Knowing this truth prepares you to use abstractions wisely, without believing they can protect you from the details forever. Every programmer begins with the idea that perfect code is possible. If you think carefully enough, test thoroughly enough, and plan every detail, you can release a system without flaws. This belief lasts only until you work on real projects. No matter how careful you are, every system ships with flaws. Some are minor annoyances, some are hidden for years before they appear, and some break in ways you never imagined. The real skill is not in chasing perfection but in writing code that fails gracefully when the flaws show themselves. Consider the case of a payment system. You test it with valid credit card numbers, expired cards, and cards with insufficient funds. Everything looks fine. Then one day a customer enters a card number with an unexpected format because their bank issued a new type of card. Your validation logic rejects it, even though it is valid. The user cannot pay, and the system fails. You did not predict this input, and you could not test for it because you did not know it existed. The failure was inevitable, but how you handle it matters. If the system provides a clear error message and logs the failure for investigation, the damage is limited. If the system crashes without explanation, both you and the customer suffer. This shows the value of graceful failure. Another scenario is network communication. You might build a service that calls an external API to fetch data. In development, the API is always available and responds quickly. In production, the API may slow down, time out, or return errors you did not expect. No amount of testing can cover every possible network hiccup. The code cannot be perfect because the environment itself is not perfect. The way forward is to build with failure in mind. You add retries with backoff. You handle timeouts with sensible defaults. You log the issue and continue running rather than halting the whole system. In this way, you do not eliminate flaws but contain them. Hardware also introduces flaws you cannot predict. A disk may fail mid-write, leaving corrupted data. A memory chip may flip a bit due to a rare cosmic ray. These events are not common, but they happen often enough in large systems to matter. You cannot write code that prevents them, but you can write code that reacts well. Databases use replication so that if one server fails, another holds a copy. File systems use checksums to detect corruption. These designs accept that perfect operation is impossible and aim to recover from the inevitable imperfections. Even logic errors in your own code prove the same point. You may reason through a feature, write tests, and deploy it with confidence. Then a user tries a sequence of actions you never considered, and the system behaves in a way you did not intend. Suppose you design a booking system for flights. You test booking, cancelling, and rescheduling, but a user books two overlapping flights, cancels one, and then tries to reschedule the other. The code did not account for this path, and now the state is inconsistent. The flaw was not a lack of care, but the impossibility of predicting every path a real user might take. Again, the value lies in whether the system fails silently, corrupting data, or whether it detects the inconsistency and alerts you. Some developers push back by saying more tests will solve the problem. Tests do help, but they cannot prove correctness in every case. You can only test for what you imagine could break. Bugs often live outside your imagination. Think about the early days of the internet, when engineers designed protocols assuming packet loss was rare. They built systems accordingly. Then the real world exposed flaws because packet loss was common on wireless networks. The protocols had to change. No test suite written at the time could have covered this because no one imagined the environment changing in that way. Perfect code was never possible. User behavior is another source of imperfection. People use systems in ways developers do not expect. A form might ask for a name, and someone enters a script instead of text, triggering a security flaw. A file upload system might allow a user to upload a file so large it overwhelms storage. A chat app might handle emojis poorly and crash on certain devices. You cannot anticipate every edge case. Users are creative, and their creativity exposes the limits of your code. You cannot control that, but you can control whether your system collapses or handles errors in a controlled way. Complex interactions between components also make perfection unreachable. Modern systems are built from many parts: web servers, databases, caches, queues, third-party services, and client applications. Each part might work well on its own, but their interactions create emergent behavior you did not design. Suppose a queue fills up faster than consumers can process it. The system slows down, requests pile up, and timeouts spread across services. No single piece of code is broken, yet the system as a whole fails. Designing for graceful degradation, such as shedding load, prioritizing essential tasks, or giving clear errors, becomes essential. Security further proves that perfection does not exist. Every year, new vulnerabilities appear in software once thought secure. Attackers find ways to exploit assumptions that seemed safe. A buffer overflow here, an injection there, or a side channel leak in hardware, all reveal flaws that no one predicted. Writing secure software is not about eliminating all flaws, it is about reducing known risks and responding quickly when new ones surface. It is about isolating failures so they cannot spread and about patching systems with minimal disruption. Security work is a reminder that no code is flawless. Think about the systems that run critical infrastructure, like air traffic control or medical devices. They undergo rigorous testing and certification, yet flaws still appear. Engineers accept this and focus on redundancy, monitoring, and fallback systems. A plain software does not assume perfection, it assumes failure will happen and prepares multiple backups. That mindset is what keeps passengers safe. The same principle applies to every other system, whether it runs a hospital, a bank, or a chat application. The aim is resilience, not perfection. Your perspective as a developer changes once you accept that perfect code does not exist. You stop chasing the impossible and instead learn to design for failure. You write logs that explain what went wrong. You add alerts that notify the right people. You build systems that keep running in a degraded state rather than shutting down entirely. You validate input to prevent obvious errors, but also assume that invalid input will still arrive. You create recovery tools to repair broken data. Each of these steps is a response to the truth that flaws are not exceptions but normal events. In smaller ways, this principle applies to daily coding habits. You learn to check return values rather than assuming success. You learn to handle exceptions rather than letting them crash the program. You design APIs that communicate errors clearly rather than hiding them. You write code in a way that future changes can be made without breaking everything. These practices all flow from the same idea: flaws are inevitable, but failure does not have to be catastrophic. Perfect code does not exist because software lives in an imperfect world. Networks fail, hardware breaks, users surprise you, and interactions grow too complex to predict. You cannot write code that avoids every flaw, but you can write code that survives them. The real measure of skill is not whether your system is flawless, but whether it can fail in ways that keep it useful, understandable, and recoverable. When developers talk about testing, the conversation often drifts toward confidence. The idea is that if you test enough, you can prove your system is correct. You write unit tests for each function, integration tests for how components work together, and end-to-end tests for the full flow. Passing tests give a sense of safety, but the truth is that testing can never prove correctness. You can only test what you imagine could break. Bugs often hide outside the reach of your imagination, and they appear only when the system faces conditions you never thought to include in a test. Think about a login system. You write tests to check that valid credentials succeed and invalid ones fail. You add tests for expired passwords and locked accounts. Everything passes, so you feel confident. Then a user tries to log in with an emoji in their username, and the system crashes. You never wrote a test for this because you did not think of it. The bug was real, but it lived outside the scope of your test cases. This shows that tests only confirm the cases you already considered. They do not guarantee there are no other cases you missed. Another example is concurrency. Suppose you build a function that updates a bank account balance. You test deposits, withdrawals, and edge cases like withdrawing the full amount. The tests pass, but when two withdrawals occur at the same time in production, both read the old balance before updating, and the account ends up with less money than it should. You did not test for simultaneous requests because your imagination focused on single-threaded logic. The correctness of your function was never proven by the tests, only suggested within a narrow set of conditions. Testing frameworks encourage the belief in correctness because green check marks feel definitive. Yet these marks only mean the code works for the scenarios you wrote down. You cannot write tests for infinite possibilities. Inputs can vary in ways you do not expect. Networks can fail in patterns you did not simulate. Users can perform actions in sequences you never considered. Each unknown creates a gap in coverage. Real correctness would require exploring all possible paths, which is not practical for anything beyond trivial programs. Consider integration with third-party APIs. You may write mock tests to simulate their responses. You cover expected success, error codes and timeouts. But what if the third-party system sends malformed JSON one day due to a bug on their side? Your mocks did not cover that, so your system crashes. The tests said you were safe, but they never reflected reality. The gap comes from the difference between what you imagined could go wrong and what actually happens in the wild. Some bugs arise not from a single function, but from the interaction of multiple components. Imagine a shopping cart system with separate services for inventory, pricing, and checkout. Each service passes its own tests, but under load, the inventory service lags by a second, and customers are able to check out items that are already sold out. No unit test caught this because the problem appeared in the timing of interactions, not in isolated functions. You may add integration tests after the fact, but those are still based on issues you now know about. Unknown interactions remain untested, waiting to appear later. Testing can even create a false sense of security. A team may reach high coverage numbers and believe the system is correct. They celebrate the percentage without realizing that many tests only check simple cases. Coverage metrics show that code paths were executed, not that they were tested meaningfully. Running a function with default input might mark lines as covered, but it does not prove the function behaves correctly under real-world conditions. The illusion of correctness is dangerous because it hides the gaps that still exist. The environment itself introduces surprises that tests rarely capture. You may test your code on a development machine where everything is controlled, but production brings different operating systems, library versions, network latency, and hardware constraints. A function that runs fine on your laptop may run out of memory on a small server. A query that finishes instantly in a test database may slow down on a production table with millions of rows. Tests did not fail, but correctness was never proven under real conditions. User behavior is another wild card. People interact with systems in unpredictable ways. A form may ask for a birth date, and someone enters a date from the year 1700. A file upload feature may receive a video 10 times larger than expected. A chat system may see a flood of messages from automated bots. Developers often fail to imagine these scenarios, so tests never include them. When the system fails, it is not because the developers were careless, but because human imagination cannot cover the endless creativity of users. Even when you try to expand your imagination, the number of possible cases grows too large. Take a simple function that takes 3 inputs, each with 10 possible values. That is already 1,000 combinations. Adding more inputs or states makes exhaustive testing impossible. You select cases that seem most important, but by doing so you admit that you cannot test them all. Somewhere in the untested combinations, a bug may hide. Testing reduces risk, but it does not erase it. Formal methods exist to mathematically prove certain programs correct. These work in limited domains such as cryptographic protocols or safety-critical systems, but for general software the complexity is too high. Proofs require enormous effort and cover only narrow parts of the system. Most of the time developers rely on testing because it is practical, but they must remember its limits. Testing increases confidence but does not equal proof. The real value of testing lies in catching common mistakes early and in making future changes safer. When you refactor code, tests help confirm that behavior stayed the same for known cases. But even here, the coverage is bounded by imagination. If you never wrote a test for a certain edge case, the refactor may break it without warning. This is why experienced teams treat tests as tools, not guarantees. They complement tests with monitoring, logging, and defensive coding. They assume some bugs will reach production and prepare to detect and handle them. You can see this philosophy in resilient system design. Services often include fallbacks when external calls fail, not because tests missed something, but because real-world conditions always create failures. Systems include retries, circuit breakers, and rate limits to survive events that no test suite could fully simulate. The mindset shifts from proving correctness to managing imperfection. Testing plays a role, but it is only one part of a larger strategy. When you write code, you cannot think of testing as the final word on correctness. It is a safety net woven from your imagination. It catches the mistakes you thought to look for, but it cannot catch the ones you never considered. The unknown remains, and that is where bugs wait. Understanding this helps you respect tests for what they are: valuable, necessary, but limited. When you begin building software, the focus is on making something that works at all. If 10 users can sign up, log in, and use the service, the system feels successful. You may store everything in a simple database, run it all on one server, and write straightforward code. At that scale, the design seems fine, but scale has a way of exposing weaknesses. A solution that works well for 10 users can collapse under the weight of 10,000. Efficiency and architecture matter most. When scale forces you to care, take the case of a chat application. At small scale, you can store every message in a single table and query it directly for each conversation. With 10 users sending a few messages each day, performance looks instant, but as soon as you grow to thousands of users sending millions of messages, the same approach slows to a crawl. Queries that once took milliseconds now take seconds. Indexes cannot keep up, and the database server becomes a bottleneck. The design was not wrong at the start. It was enough for the problem then, but growth revealed the limits, and now you must rethink the architecture. Scaling changes not just databases, but also how you think about servers. Running everything on one machine is easy. You deploy once, restart when needed, and handle issues directly. At 10 users, the load is light. At 10,000, the same machine runs out of CPU, memory, or disk space. Requests begin to fail. To survive, you must distribute the system across multiple machines. That means dealing with load balancing, replication, and fault tolerance. Each layer introduces new complexity. You must decide how to split traffic, how to synchronize data, and how to handle partial failures. These problems did not exist at small scale, but scale forces you to confront them. Consider file storage. A small application might store uploaded images on the local disk of the web server. With a few users, this works fine, but when thousands upload files, the disk fills up, backups become painful, and serving files slows the server. At that point, you cannot treat storage as a local problem. You must move to dedicated systems like object storage or distributed file systems. Scaling forces the separation of concerns. Storage, compute, and networking must be designed as independent but connected services. Even code that seems harmless, at small scale, can break under load. Imagine writing a function that fetches a list of users, sorts them and filters them in memory. With 10 users, the function completes instantly. With 10,000, the memory footprint grows and the response time spikes. At 100,000, the server may run out of memory. The logic did not change, but the input size did. Scale turns a trivial function into a serious problem. The fix may involve pushing filtering into the database or using pagination. These changes are unnecessary at 10 users, but essential at 10,000. Network traffic illustrates another shift. With a handful of users, you can send frequent updates or even poll the server often. The traffic is low, and bandwidth is cheap. At scale, constant polling becomes wasteful. Thousands of clients pinging the server create massive overhead. You must move to more efficient designs like WebSockets, long polling, or event-driven notifications. Again, the small-scale solution was fine when traffic was low, but scaling forces you to care about efficiency. Scaling also changes your view of reliability. At small scale, downtime may go unnoticed. If 10 users cannot log in for 5 minutes, it is a minor annoyance. At 10,000 users, the same downtime may spark support tickets, lost revenue, and damaged trust. A single point of failure that felt harmless before now becomes unacceptable. You must build redundancy, monitoring, and alerting. Failures must be detected quickly and recovered from automatically. The expectation of reliability rises with scale, and architecture must adapt. Think about logging. With a small system, you can log everything to a single file and read it when needed. At scale, logs grow too large for one file. Searching them becomes impossible, and storing them consumes resources. You must introduce centralized logging systems, indexing and retention policies. What was once a small debugging tool becomes an entire infrastructure problem. Scale forces you to manage information differently. Security concerns also change with growth. 10 users may never try to exploit your system. At 10,000, you attract attention. Attackers may probe for weaknesses, bots may flood your endpoints, and abusive patterns may appear. Suddenly, rate limiting, authentication hardening, and monitoring become essential. Security was always important, but scale makes the risks visible and immediate. Systems must be designed to withstand not only honest use, but also malicious attempts at abuse. Even organizational aspects reflect this truth. At small scale, one developer may understand the whole system. They can hold it in their head and make quick changes. At scale, no one person can understand everything. Teams must specialize, and documentation becomes critical. Processes like code review, continuous integration, and deployment pipelines shift from optional to necessary. The complexity of people working together grows alongside the complexity of the system. Scale forces discipline not just in code, but in collaboration. A practical example comes from social media platforms. A site that begins as a small community forum may run fine with simple tools, but once millions join, features that once worked start to break. Search becomes too slow, feeds cannot update in real time, and moderation struggles to keep up. Each part of the system that scaled linearly now becomes a bottleneck. The company must invest in distributed search engines, caching layers, and content moderation tools powered by automation. Scaling forces the evolution of both technology and processes. Not every system needs to be built for massive scale from day one. Over-engineering early can waste time and delay progress. A startup with 10 users does not need the same architecture as a global platform, but it is useful to know that growth changes the game. What feels acceptable today may collapse tomorrow. This awareness helps you design with an eye toward what might come. You keep code modular, avoid unnecessary coupling, and choose tools that can stretch further. You do not optimize prematurely, but you remain prepared for the moment when scale forces you to care. Scaling reveals that software is not just about logic, but about capacity. It is about how much data you can store, how many requests you can handle, how fast you can respond, and how resilient you are when parts fail. A design that seems solid in the small can collapse in the large. Developers who understand this principle write with humility, knowing that success brings not only more users but also more problems. Each new order of magnitude introduces new challenges. Scaling changes everything, and when the time comes, efficiency and architecture are no longer optional details, but the foundation of survival. Every developer has faced the moment when code runs fine on their machine but fails somewhere else. You run your program, the tests pass, and everything looks solid. Then you deploy it to a server or hand it to a teammate, and it breaks. The phrase "works on my machine" has become a joke in the industry, but behind the humor lies a hard truth. Code does not run in isolation. It depends on environments, operating systems, libraries, configurations, and sometimes even hardware. What works in one place may fail in another, and luck is never enough to guarantee consistency. The way forward is reproducibility, not hope. Imagine you are building a web service that relies on a database driver on your laptop. The driver is version 2.1. On the server, it is version 2.0. The minor difference seems harmless, but one query behaves differently because of a bug that was fixed in 2.1. The code you wrote works locally but fails in production. Nothing in your logic changed, yet the outcome did. The problem lies in the mismatch of dependencies. Without control over versions, your environment shapes your results more than your code does. Operating system differences create similar problems. Suppose you write a script that manipulates file paths on your Windows machine. The script uses backslashes in paths. On a Linux server, paths use forward slashes. The script fails, not because your logic was wrong, but because the environment changed. Or consider case sensitivity in file systems. A file named data.txt may load fine on macOS but fail on Linux where case matters. These differences lurk beneath the surface until the code leaves your machine. At that moment, "works on my machine" loses all meaning. Configuration drift is another common source of failure. You may run a local server with default settings. In production, an administrator has tuned timeouts, memory limits, or thread pools. Your code assumes a default that no longer exists. The system misbehaves and debugging becomes painful because nothing looks wrong in the source. The issue comes from environment configuration, not from the code itself. Without reproducible environments, these mismatches are inevitable. Dependencies spread the problem further. Modern software rarely runs without libraries and frameworks. Each one has its own versions and subdependencies. Package managers help, but they are not perfect. A library may release a patch that changes behavior in subtle ways. If your teammate installs dependencies a week later than you, they may receive a slightly different version. The result is that their environment differs from yours even though you both used the same command. This leads to hours spent trying to reproduce a bug that does not appear on your machine. Lock files and version pinning help, but they require discipline to use consistently. Containers change the landscape by offering reproducibility. With tools like Docker, you can define the entire environment, operating system, libraries, dependencies, and configurations in a single file. Anyone who builds the container gets the same environment, no matter what machine they run it on. This reduces the chance of surprises between development and production. A web service packaged in a container behaves the same on your laptop, in testing and in deployment. Containers do not remove all problems, but they shrink the gap between machines. They replace luck with predictability. Virtual machines and container orchestration systems push the idea further. With Kubernetes, for example, you do not just define the environment of one container. You define how containers interact, scale, and recover. The system ensures the state remains consistent across nodes. This approach acknowledges the truth that environments betray you unless you control them. Rather than saying works on my machine, you build so it works in the same way everywhere. Reproducibility is not only for deployment, but also for testing. Continuous integration pipelines run code in clean environments each time. They install dependencies from scratch, apply configurations, and run tests. If a test fails in the pipeline but not on your laptop, that points to an environmental difference. The pipeline catches issues earlier, before they reach production. Without such pipelines, developers rely on personal setups which vary too widely to give reliable results. Even hardware plays a role in breaking assumptions. A program that runs fine on a powerful laptop may fail on a smaller server with less memory. A concurrency bug may hide on a single-core machine but appear on a multi-core system. Timing issues may never show up in your local tests, but emerge under heavy production load. These failures do not mean the code was never tested. They mean the test environment did not reflect the real world. The closer you bring your development and production environments, the fewer surprises you face. Think about database migrations. On your machine, you apply a schema change to a small test database, and it finishes in seconds. In production, the same migration runs on millions of rows and locks the table for hours. Your machine did not reveal the flaw because the state of the environment was too small to show it. Reproducibility in this case means testing against production-like data, not only production-like software. Scale itself becomes part of the environment that must be considered. Debugging works on my machine issues often consumes more time than writing the feature itself. Teams lose hours trying to reproduce a bug that only appears under certain conditions. The log files from production look different from the ones generated locally. A dependency behaves differently across versions. An environment variable is missing in one place but present in another. Each clue points to the truth that environments matter as much as code. Without reproducible setups, the same code can act like two different programs depending on where it runs. This is why experienced teams treat infrastructure as code. Instead of configuring servers by hand, they define everything in scripts and configuration files. Tools like Terraform or Ansible ensure that environments can be recreated from scratch, exactly the same each time. This prevents drift and removes the human element of "but I configured it this way last week." The goal is to eliminate surprises by making environments explicit, not hidden behind personal setups. The phrase "works on my machine" survives as a joke because it reflects real frustration. It highlights the gap between what a developer sees locally and what happens elsewhere. But in serious work, relying on local success is not enough. The only way to move past the joke is to build systems that behave the same across machines, teams, and deployments. Containers, version pinning, automated pipelines, and infrastructure as code all exist for this reason. They acknowledge that environments betray you if left unmanaged, and they replace chance with reproducibility. When you start programming, it is easy to focus on the language itself. You learn the keywords, the syntax, and the unique features that make one language feel different from another. You may even argue that one language is better than all others, because of its style or its libraries. But the more time you spend in software, the clearer it becomes that the language does not matter as much as you think. The syntax changes, but the principles stay the same. Loops, recursion, functions, and design patterns exist in every language, and those are the tools that shape how you solve problems. Think about a simple task like summing the numbers in a list. In Python, you might use a for loop or the built-in sum function. In JavaScript, you might use reduce. In C, you write a loop with an index and a counter. The surface details differ, but the idea is the same. You iterate through values and accumulate a result. Once you understand iteration, you can apply it in any language. The keyword for or while might look slightly different, but the thinking does not change. A developer who knows the principle of iteration can move between languages without much trouble. Recursion shows the same point. Many languages let you solve problems by calling a function inside itself. You might write a recursive factorial function in Python, Java, or Haskell. The syntax differs, but the concept of breaking a problem into smaller subproblems stays constant, whether you use curly braces, indentation, or arrow syntax. The core idea of recursion follows the same reasoning. Once you learn recursion as a principle, you can use it anywhere, even in a language where you rarely need it. The language is only a wrapper around the deeper idea. Data structures make the case even stronger. Arrays, linked lists, hash maps, trees, and graphs exist in nearly every language. The names may change slightly, and the libraries may offer different methods, but the behavior is universal. A hash map in JavaScript looks like an object or a map. In Python, it is a dictionary. In Java, it is a hash map. The syntax changes, but the concept of key-value storage does not. When you understand how a hash map works, you know how to use it in any language. You think about collisions, lookups, and storage, not about whether the method is called get or fetch. The same holds for design patterns. The singleton pattern, the observer pattern, or the factory pattern are not bound to any specific syntax. They describe ways of organizing code to solve common problems. You can implement an observer in Java with interfaces, in Python with functions and callbacks, or in JavaScript with event emitters. Each looks different, but the principle is the same. One object broadcasts changes, and others subscribe to receive them. Learning the pattern matters more than memorizing how to write it in a given language. This becomes clear when you switch jobs or projects. You may have spent years working in Java and then moved to a team that writes everything in Go. At first, the syntax feels foreign. The way you declare variables or write loops is new, but within a few weeks you begin solving problems because the principles carry over. You still break tasks into functions, still use loops and conditions, still think in terms of data structures. The specific keywords fade in importance. What matters is how you think about the problem. Even paradigms like object-oriented programming or functional programming extend across languages. Java and C# emphasize classes and objects, while Haskell and Clojure emphasize functions and immutability. Yet functional ideas like higher-order functions exist in JavaScript, and object-oriented ideas exist in Python. The borders between paradigms blur because the principles are not tied to one place. If you understand encapsulation, composition, or immutability, you can apply them anywhere. You may write them in different styles, but the thinking stays consistent. Consider debugging. When you trace through a bug, you ask questions like, where did this variable change? What function produced this result? And how did this value propagate through the system? Those questions are not tied to language syntax. They are tied to the principles of program flow, state, and data. A developer who understands those principles can debug in any language, even one they have not used before. They may need to learn the commands of the debugger or the print syntax, but the core reasoning is transferable. This perspective explains why experienced developers often pick up new languages quickly. They already know the foundations. They understand loops, recursion, data structures, and patterns. Learning a new language means learning its quirks, how it handles memory, how it manages types, what standard libraries it provides, but those are surface details. The deeper knowledge stays the same. This is also why computer science education often emphasizes algorithms and data structures rather than one specific language. Languages come and go, but the principles endure. Libraries and frameworks sometimes give the illusion that language is everything. You may feel tied to Python because of its data science libraries, or to JavaScript because of its web frameworks. But even here, the language is less important than the underlying tools. Pandas, for example, helps you manipulate data frames. You can find similar libraries in R, Julia, or other languages. React helps you manage UI components, but the pattern of stateful components exists elsewhere too. If you learn the principle, moving between languages and tools becomes easier. It is also worth noting that syntax can sometimes distract from real thinking. Beginners may spend hours worrying about where to put semicolons or how to format indentation. Those details matter for getting code to run, but they do not teach you how to structure logic or reason about state. Once you understand that the core ideas stay the same, syntax becomes less intimidating. You stop seeing languages as separate worlds and start seeing them as different dialects of the same discipline. One way to illustrate this is with sorting. You can write a bubble sort in C, a quick sort in Python, or a merge sort in JavaScript. The language changes, but the algorithmic ideas stay constant. You think about dividing arrays, comparing values, and merging results. Once you grasp the principle, the syntax is just a tool for expressing it. The real power comes from knowing how sorting works, not from knowing whether to write for I equals sign 0, ICNI++, or for I in range. This does not mean language choices never matter. Some languages are better suited for certain tasks. C is close to hardware and used in systems programming. Python has a rich ecosystem for data science. JavaScript dominates in web browsers, but even here the shift is about tools and ecosystems, not about fundamental principles. A developer who understands concurrency can move from Java threads to Go routines. A developer who understands memory management can adapt from manual allocation in C to garbage collection in Java. The skill is transferable because it rests on concepts, not on keywords. Over time, the number of languages you know becomes less important than the number of principles you have mastered. Languages rise and fall in popularity. 10 years ago, many teams wrote in PHP. Today, many write in TypeScript. 10 years from now, something else may dominate. If your knowledge is tied only to a language, you must start fresh each time. If your knowledge is tied to principles, you can adapt to whatever language the future brings. That is why syntax matters less than understanding loops, recursion, data structures, and design patterns. They are the constants in a field where everything else changes. When you first learn programming, it is easy to get caught up in the tools of the moment. A new framework launches, a library promises faster results, and everyone seems to rush toward it. Frameworks and libraries solve real problems, and they can save time. But they come and go, they rise in popularity, then fade when something new takes their place. What stays the same are data structures. A hash map, a tree, or a graph algorithm does not lose relevance when a framework gets abandoned. These building blocks outlive every tool built on top of them because they solve fundamental problems in computation that never change. Think about hash maps. They give you constant time access to data using keys. No matter the language or framework, this idea is powerful. In Python, you use dictionaries. In JavaScript, you use objects or maps. In Java, you use hashmap. The syntax and naming differ, but the principle remains the same. When you need to store and retrieve values efficiently, a hashmap is the right tool. Frameworks may offer helpers that wrap this behavior, but under the surface, the same concept powers them. Long after a web framework loses support, the ability to choose a hashmap for the right job remains relevant. Trees show the same staying power. A binary search tree organizes data so you can insert, search, and delete efficiently. A balanced tree like a red-black tree or AVL tree guarantees performance even as the dataset grows. You may never implement these from scratch in a production system, but many tools depend on them. Databases rely on B-trees to index records. File systems use tree structures to organize directories. Frameworks may hide this detail, but it is there, working behind the scenes. If you understand how trees function, you can reason about performance and make better choices. The framework may vanish, but the tree endures. Graphs are another timeless structure. They represent relationships between entities, people connected in a social network, cities linked by flights, or devices communicating in a network. Graph algorithms like Dijkstra's for shortest paths or depth-first search for traversal solve problems across fields. A new library may give you functions to run these algorithms, but the principles are older than most programming languages in use today. A developer who understands graphs can adapt to any tool because the logic of nodes and edges never changes. The frameworks for handling graphs may shift, but the algorithms remain useful. Contrast this with frameworks. 10 years ago, many developers used frameworks like Struts for Java web development. Today, few would recommend starting a new project with it. JavaScript frameworks have seen cycles too. Backbone.js was once popular, then AngularJS, then React, and now newer contenders. Each framework promises better patterns, better performance, or better tooling, but they all fade eventually, replaced by the next wave. A developer who ties all their knowledge to a framework must relearn when the trend changes. A developer grounded in data structures can move between frameworks because the underlying principles are stable. Imagine a scenario where you must speed up a search feature in a large dataset. If you only know the framework's default query methods, you may struggle when they slow down. But if you know data structures, you can recognize that building an index using a hash map or a tree will improve performance. You may use the framework's tools to implement it, but the insight comes from understanding the structure. This ability does not expire when the framework does. It stays with you and applies in every system you build. Another example is caching. Many frameworks provide caching layers to reduce database load, but knowing why caching works comes from understanding data structures. A cache is often just a hash map with policies for eviction like least recently used LRU. If you know how hash maps work and how to implement an eviction policy, you understand what the framework is doing behind the scenes. If the framework fails or you move to another one, the principle remains. The data structure knowledge lets you rebuild or adapt without depending on a specific tool. Data structures also matter in interviews and problem solving because they test reasoning rather than memorization. A framework can be learned in weeks, but data structures take practice to master. Employers know frameworks shift, so they focus on algorithms and data structures. They want to see if you can choose the right tool for a problem. If you know how to use a priority queue for scheduling or a graph traversal for dependency resolution, you can solve problems across languages and frameworks. This is why technical interviews rarely ask about frameworks but often ask about arrays, linked lists, and trees. Think about performance at scale. Suppose you build a service that handles millions of requests. A poor choice of data structure can make it collapse. Using a list when a hash map is needed may turn constant time lookups into linear time searches. At small scale, this may not matter. At large scale, it becomes a bottleneck. Frameworks may help with boilerplate, but they cannot fix a fundamental mismatch in data structure choice. The ability to pick the right structure is timeless, and it separates robust systems from fragile ones. Even in new fields like machine learning, data structures remain central. Neural networks are built on matrices and tensors, which are specialized data structures. Efficient training depends on how data is stored and accessed. Libraries like TensorFlow or PyTorch may dominate now, but they could be replaced in the future. The underlying principles of tensors, graphs, and arrays will not vanish. A developer who understands them can adapt to any new tool. Frameworks often create layers of abstraction that hide data structures. This can make development faster at first, but leaves you blind when problems arise. For example, an ORM may let you write queries without thinking about indexes. At small scale, this works. At large scale, queries slow down, and you must understand B-trees or hash indexes to fix them. The abstraction leaked, and only knowledge of data structures helps you move forward. Frameworks promise simplicity, but when they fail, the timeless structures remain the path to solutions. There is also a cultural aspect. Frameworks often build communities that share tutorials, plugins, and patterns. This support is valuable but temporary. When the community moves on, the resources shrink. In contrast, data structures are universal. The knowledge does not depend on a community staying active. A graph algorithm learned today is the same one described decades ago. The material remains relevant regardless of trends. That stability is rare in technology, and it gives data structures their enduring value. The life cycle of technology proves the point again and again. Languages change, frameworks come and go, and libraries are abandoned. But every generation of software still needs arrays, queues, trees, and graphs. They remain the foundation for solving problems. They form the mental toolkit that lets you adapt no matter what tools surround you. Developers who understand data structures invest in skills that last beyond the trends, and that knowledge outlives every framework. When you build software, it is natural to think of user input as helpful information. A name in a form field, a search query, or a file upload feels like data you can trust. But in practice, input is the most dangerous part of any system. Every piece of input carries risk because it can be manipulated. Some users make mistakes, others push limits, and some act with intent to break or exploit. The safest mindset is to treat all input as hostile. Security is not about trusting what arrives, but about defending against what might be hidden inside. It is paranoia made practical. Imagine a login form that accepts a username and password. If you take that input and build a database query directly, an attacker can insert special characters to alter the query. This is SQL injection. Instead of fetching one user, the query may return all users or even delete data. The system invited the attack by trusting the input. A developer who assumes input is hostile uses parameterized queries or stored procedures, so the database interprets values as data, not as commands. The defense comes from refusing to trust what the user typed. Cross-site scripting, or XSS, shows the same principle in web applications. Suppose you build a comment section where users can post text. If you display the text directly in a browser, an attacker can insert JavaScript instead of plain text. When others read the page, the script runs in their browsers. It may steal cookies, redirect pages, or perform actions as the victim. The root problem is trusting that the comment is harmless text. The fix is to escape or sanitize input before displaying it, so scripts cannot run. Again, the mindset of treating input as hostile prevents harm. File uploads illustrate the danger in another way. A system may allow users to upload images. If the developer trusts the input, they may save the file as is and serve it later. An attacker could upload a script disguised as an image and trick the server into executing it, or they could upload a massive file to exhaust disk space. A cautious developer inspects the file type, checks the size, stores it in controlled directories, and never executes it. Hostile input is expected, so protections are built in. Even simple forms can cause problems. A field asking for an age might receive negative numbers, fractions, or values larger than possible. A careless system may accept them and fail when calculations break. Attackers may exploit this to crash the system or bypass restrictions. Treating input as hostile means validating ranges, types, and formats. It means assuming the field will be used incorrectly and writing code that handles it safely. Network input deserves the same suspicion. APIs often receive JSON or XML from clients. Attackers may craft payloads that are malformed, oversized, or designed to exploit parsers. XML external entity attacks, for example, trick a parser into exposing files or making requests to internal systems. The defense is to configure parsers securely and validate input against expected schemas. No matter how much trust you place in a client, you assume it can send something malicious. Some developers argue that not all users are attackers, so paranoia seems excessive, but the truth is that many exploits happen by accident or through automated tools. A bot scanning the internet does not care about your system specifically. It sprays common attacks everywhere. If your system accepts input without defenses, it will eventually be hit. Even honest users can trigger flaws by pasting unexpected characters, switching languages, or using devices with unusual settings. Treating input as hostile is not about distrusting people. It is about acknowledging that mistakes and attacks both happen. Authentication systems show the need for this mindset. A password field must never be trusted as clean input. Users may include characters that break encoding. Attackers may try to inject scripts or test billions of guesses. Systems must hash passwords securely, rate limit attempts, and reject malformed inputs. Without those steps, the system relies on hope rather than defense. By assuming passwords are hostile input, developers protect against both clumsy mistakes and deliberate attacks. Logs are another overlooked vector. If you log raw input for debugging, attackers can insert escape characters or log-breaking text. This may make logs unreadable or even exploit log viewers. Treating input as hostile extends even to debugging tools. Sanitize before storing. Defenses apply not only to user-facing features, but to every place input travels. Consider APIs exposed to other services. A payment gateway may trust that merchants send valid data, but a compromised merchant system can send manipulated requests. If the gateway trusts them, fraud becomes easy. By validating amounts, checking signatures, and verifying data, the gateway treats input as hostile even when it comes from supposed partners. Security requires assuming that trust can be broken. This principle is not only about blocking attacks, but also about limiting damage. Input validation and sanitization reduce the attack surface. Rate limiting prevents floods of malicious requests from overwhelming the system. Encoding prevents code injection from being executed. Each step assumes that the next input could be the one designed to break you. By expecting the worst, you prepare for it. A classic example is email input. A form may ask for an email address. A naive system only checks that the field is not empty. Attackers insert code or control characters. Smarter systems check for the structure of an email. Stronger ones use libraries to validate formats and reject invalid domains. The strongest go further by confirming the email through a link. Each layer accepts less trust. Each layer treats the input as hostile until proven otherwise. Internationalization also creates tricky cases. Unicode allows many characters that look alike. Attackers can use homograph attacks, creating domain names or usernames that appear identical but are different strings. If your system trusts that two names looking the same are the same, you may give privileges to the wrong user. Treating input as hostile means recognizing that even text that looks harmless may hide tricks. Normalizing or restricting inputs helps defend against this. Input length is another area where trust fails. If you assume a username will always be under 50 characters, an attacker may send 10,000 characters. This may overflow buffers, crash databases, or consume memory. Systems that trust input sizes break under load. Systems that treat input as hostile enforce limits and reject or truncate safely. Hostility is not about intent, it is about preparing for extremes. Even when you trust yourself, input from your own systems can become hostile. A microservice sending data to another may break due to a bug. If the receiving service trusts it blindly, the bug spreads. If it validates the input, the damage stops. Hostile input is not only from attackers but also from software errors. The same defensive posture protects against both. The mindset of hostile input changes how you design. Instead of asking whether you can trust, you assume you cannot. You build filters, validations, encodings, and checks as default steps. You do not skip them because the input comes from a known user or a familiar service. You accept that any entry point can become a channel for exploitation. Security is not paranoia without reason. It is paranoia turned into practice, a discipline that expects the worst from input so systems remain safe even when the worst happens. When a developer writes code, it often stays within a single project or a single team. You can change functions, rename variables, or rewrite entire modules without worrying too much, as long as you update everything that depends on them. But when you publish an API, the rules change. An API is a contract with other developers. Once you release it, you lose control over how it is used. Someone, somewhere, will build their own system on top of it, and from that moment forward, the API is no longer just your tool. It becomes an external promise. Breaking that promise can break businesses. That is why APIs are forever. Imagine you release a simple REST API that allows users to fetch product information. The endpoint returns a JSON object with a product name, description, and price. A developer at another company builds an application that relies on this endpoint to show products in their store. Months later, you decide to rename the field price to cost because it sounds clearer. On your side, this looks like a harmless change. But the application, depending on your API, now crashes because it is still looking for price. You did not just change a word, you broke another company's system. For them, the API was a promise that price would always exist. This is why small details matter. Once an API is public, versioning exists to deal with this problem. Instead of changing the existing API, you release a new version with your changes, such as V2. Users of V1 can continue using the old fields, while others move to V2 when they are ready. But even with versioning, you carry the responsibility of supporting older versions for a long time. Businesses often cannot upgrade quickly. They may have legacy systems, limited budgets, or strict validation processes that slow adoption. If you shut down V1 too soon, you force them into emergencies. They may lose functionality, revenue, or customer trust. Supporting old versions costs time and resources, but it is part of the commitment of publishing an API. Consider authentication methods as another example. Suppose your API initially allows basic authentication with a username and password. Later, you want to improve security by requiring O tokens. If you immediately cut off basic authentication, every client that has not migrated yet breaks. Developers who built against your API may not even be aware of the change until their systems fail in production. A safer path is to introduce OTOT while still supporting basic authentication for a period of time, giving others time to adapt. Even then, communication and clear timelines are essential. The principle remains: when you publish an API, you must assume others depend on it in ways you cannot fully predict. Some APIs become so widely adopted that they outlive the companies that built them. Old payment APIs, shipping APIs, and even social media APIs have kept running long after they were considered outdated. Why? Because businesses built on them cannot just switch overnight. A shipping company may have warehouses, scanners, and software all tied to one API format. Replacing it would mean retraining staff, rewriting systems, and validating new processes. The cost is enormous. The provider may want to move on, but their customers force them to keep the old API alive. APIs, once released, take on a life of their own. The permanence of APIs also applies inside companies. Internal teams may publish APIs for others to use. Over time, these APIs become critical. Other teams build tools, dashboards, and services on top of them. If one team decides to change an API without coordination, it can ripple across the organization. Suddenly, other systems fail, deadlines slip, and trust erodes. Internal APIs may not face external customers, but they still carry the same responsibility. Once people depend on them, they are part of the company's foundation. This permanence explains why designing APIs requires care. It is tempting to release something quickly, thinking you can clean it up later, but later may never come, because changing it would break too many dependencies. If you rush and make poor naming choices, awkward structures, or inconsistent rules, you may be stuck supporting them forever. Many developers can point to APIs with confusing field names or illogical conventions that exist today because fixing them would break too much. Bad design lasts as long as the API does, which may be decades. Error handling in APIs shows another angle. Suppose your API returns error codes to clients. At first, you return only a generic 500 server error. Later, you decide to provide more detailed error messages, changing the format. Clients built on the old error handling now fail because they did not expect the new structure. Even improvements can break dependencies if not introduced carefully. The better path is to add new fields while keeping the old ones, so clients that rely on the old format continue to work. Supporting both paths may feel burdensome, but it is part of the commitment. Documentation also becomes part of the contract. If your API documentation states that a field is required, developers build their code accordingly. If you later decide that field is optional or remove it, clients may behave unpredictably. Even undocumented behavior can become a de facto contract. If your API responds in a certain way, and developers begin relying on it, changing it later creates problems. This is why even unintended quirks sometimes become permanent. Once observed, they may be treated as features by someone else's system. There are famous examples of this permanence. Early web browsers tolerated poorly formed HTML, and developers built websites that relied on this leniency. Later browsers had to replicate the same behavior to avoid breaking websites, even though it was technically wrong. The original behavior became a permanent part of the web because people depended on it. APIs follow the same rule. Once an interface exists and others use it, you must preserve its behavior, even if it seems flawed. For developers, this permanence can feel heavy. It means carrying legacy decisions far longer than expected, but it also teaches discipline. Before releasing an API, you think carefully about naming, structure, and behavior. You avoid unnecessary exposure of internals. You plan for versioning, deprecation policies, and long-term support. You recognize that publishing an API is not just shipping code, it is making a promise that must be kept. Businesses build trust on stable APIs. A company may decide whether to adopt your service based on confidence that the API will not break under them. If you change it carelessly, you not only break their systems but also your reputation. Developers talk, and word spreads, when an API cannot be trusted. Conversely, APIs that remain stable for years earn loyalty. People build on them without fear. This stability becomes a competitive advantage, but it comes only when you respect the permanence of the contract. The lesson is clear: once an API is published, it is forever. Someone will depend on it, sometimes in ways you never expected. Breaking changes are not just technical adjustments, they can cause real financial and operational damage. You cannot treat an API like private code. You must treat it as a public promise, one that outlives trends, frameworks, and sometimes even the systems around it. When you sit down to write code, you usually think about the present. You focus on the feature you need, the bug you must fix, or the deadline you are trying to meet. The code you produce makes sense to you in that moment. You know the context, the decisions, and the shortcuts. It feels obvious, all evocative, but time has a way of erasing that clarity. 6 months later, you return to the same file, and it looks like someone else wrote it. The variables seem vague, the functions feel confusing, and the structure makes little sense. This happens because your future self is another developer. You should write code as if you were explaining it to a stranger, because in practice, memory fades faster than you expect. You may think you will remember why you named a variable a certain way, or why you added a condition in a loop, but as projects evolve and other tasks pile up, those details vanish. When you come back, the reasons are gone, and you are left trying to reconstruct your own logic. If you had written clearer names, left a short comment, or structured the code more simply, your future self would not have to puzzle it out. The act of writing for a stranger is really the act of writing for yourself, minus the memory of today's reasoning. Imagine you are debugging a system you built a year ago. You open a function that calculates discounts for customers. It has a series of nested if statements with cryptic variable names like X, Y, and Z. At the time, you knew exactly what they meant. Now you have no idea. You spend hours stepping through the code to rediscover that X was the base price, Y was the discount tier, and Z was the final adjustment. If you had chosen descriptive names or written a brief note, the meaning would be clear in minutes. The code worked then, but it failed the test of time. You became the stranger you did not write for. This problem grows in team settings. Even if you never return to your own code, someone else will. A teammate will read your function and try to extend it. If they cannot understand it quickly, they may break it or avoid changing it altogether. In both cases, productivity suffers. Teams often say that code is read more than written, and this is true. Your future self is only one of the many readers. By writing for strangers, you are writing for teammates, maintainers, and even new hires who will join years later. Each of them approaches your work without your original context. They depend on your clarity. Consider error handling. You might throw an exception with the message, "invalid data." In the moment that feels sufficient. You know what kind of data you are processing. Months later, you or someone else sees the error in a log and has no idea what part of the data failed. Was it a missing field, a wrong type, or a value out of range? The vague message provides no help. If you had written missing required field, user_ID, or price must be greater than 0, the error would explain itself. Writing for a stranger means imagining how the message will read to someone without your present knowledge. Even formatting matters. You might compress logic into a clever one-liner because it looks neat. Later, you or someone else struggles to parse it. Splitting the code into a few clear lines with intermediate variables takes slightly more space but saves time for the reader. The machine does not care whether the code is short or long, the reader does. Since the reader is often your future self, clarity is the better investment. Documentation plays the same role. You may skip writing it because you believe the code is obvious. Later you realize it was not. A brief explanation of a function's purpose or the assumptions behind a module can guide future readers. Documentation does not need to be long or formal. A single sentence can turn a block of code from confusing to clear. For example, writing this function calculates discounts based on customer tier and active promotions sets the stage before diving into logic. Without it, the reader must infer everything from raw code. Writing as if to a stranger means leaving breadcrumbs, not riddles. Tests can also serve as communication. A well-written test shows how code is expected to behave. Your future self, looking at the test, sees examples of inputs and outputs without needing to decipher all the internals. Tests that are clear and descriptive act as living documentation. They are less about proving perfection and more about showing intention. A stranger reading your tests should understand what the code is supposed to do. Since your future self will be that stranger, tests written with clarity protect you from your own forgetfulness. Even decisions outside the code itself benefit from this mindset. You may configure a system in a certain way, choose one algorithm over another, or reject an approach that seemed promising. If you leave no record, you or others will revisit the same questions later. You may even repeat mistakes because you forgot why the original path was avoided. A short comment like, "We avoided this approach because it caused performance issues with large datasets," saves future time. These notes are not for the machine. They are for the human who no longer remembers the story, which is usually you. This principle also applies to style. Consistent style reduces cognitive load. If every file follows the same conventions, a reader can focus on logic rather than format. Style guides and linters enforce this for teams, but even alone, you benefit. In 6 months, you will not remember why you formatted one block differently from another. Consistency creates familiarity, and familiarity helps strangers, including your future self, understand more quickly. A striking example appears in legacy systems. Many companies rely on code written decades ago. The original authors may have retired or moved on. Current developers, often including those who once wrote parts of the system themselves, must treat the code as if it were written by strangers. When comments, documentation, and clear naming are missing, the cost of understanding grows. Bugs take longer to fix, features take longer to add, and trust in the system declines. Every decision to skip clarity compounds over time, creating debt that must be paid by future readers. Your own projects can become legacy faster than you expect. A side project abandoned for a year becomes foreign when you return. You stare at code you once wrote and wonder what you were thinking. You may even laugh at your old decisions. This is not because you were careless, it is because context fades. Writing as if for a stranger makes that return less painful. It gives you the chance to understand quickly and pick up where you left off. Thinking of your future self as another developer also helps you resist shortcuts. When under pressure, it is tempting to hack together a quick fix with messy code. It works now, so you move on. Later, when you or someone else must revisit it, the mess costs more time than the shortcut saved. By imagining yourself as the next reader, you see that the pain of unclear code will return multiplied. This thought encourages you to spend the extra minutes making the code understandable now, sparing hours later. Writing for a stranger does not mean over-explaining or bloating code with needless detail. It means making choices that prioritize clarity over cleverness, explicitness over ambiguity, and consistency over convenience. It means naming variables with meaning, structuring functions with readability, and leaving notes where context may be lost. It means recognizing that memory fades, context shifts, and the person reading later is not the same as the person writing now. By writing with this in mind, you protect your future self from confusion, frustration, and wasted effort. When developers talk about building software, they often focus on the code. The logic, the algorithms, the performance, and the architecture take center stage. But code on its own is never enough. Without documentation, code is a puzzle. It may run, but no one knows how or why. Clear explanations transform cryptic systems into usable tools. Documentation is not extra work you add at the end. It is part of the program itself, as essential as the functions and classes that make it run. Think about a new developer joining a project. They open the codebase and see hundreds of files. The functions have names, the classes have methods, and the logic may even be well written. But without documentation, they cannot tell what connects to what. They do not know which modules are stable and which are experimental. They do not know why certain choices were made. They may spend days reading code just to answer basic questions. If the same project had a simple README, an architecture overview, and a few notes in key places, the new developer could become productive in hours. The code did not change, but the documentation made the difference between a puzzle and a tool. Even the original author of code benefits from documentation. You may write a function today that feels obvious. You know the inputs, the outputs, and the purpose. 6 months later, you return to the same function and stare at it with confusion. Why did you handle this edge case? Why did you reject that approach? If you left no notes, you must rediscover your reasoning. Documentation saves you from that. A short comment like "this branch handles legacy data from version 1 of the API" explains what would otherwise be a mystery. You are not writing for others alone. You are writing for your future self, who will not remember the details. Consider public APIs. They may be technically sound, but without clear documentation, no one can use them. Developers depend on examples, parameter descriptions, and explanations of error codes. An API without docs is like a locked box. It exists, but it cannot be used. Good documentation, with examples and explanations, unlocks it. This is why some APIs succeed while others fail. The difference is not only technical quality, but also whether developers can understand and apply them quickly. Documentation turns potential into reality. Tests also rely on documentation. A test may pass or fail, but without an explanation of intent, its meaning is unclear. Suppose a test checks that a function returns a specific value for given inputs. If the test fails in the future, the developer fixing it may not know whether the function changed correctly or whether the test is outdated. A small note explaining why the function should behave in a certain way gives context. Documentation ensures that tests remain trustworthy instead of turning into obstacles. Frameworks and libraries show the importance of documentation at scale. A framework with great features, but poor docs may never gain adoption. Developers will not spend weeks guessing how to use it when another tool provides clear guidance. Documentation is not a side project to attract users, it is the gateway to the tool itself. The same applies inside organizations. A system may be powerful, but if only one person understands it because it lacks documentation, the system becomes fragile. If that person leaves, the system risks collapse. Documentation spreads knowledge and makes systems resilient. Some developers resist documentation, arguing that code is self-explanatory. While clean code does communicate some intent, it rarely explains the bigger picture. A function name may show what it does, but it does not explain why it exists, why it was designed that way, or how it fits into the system. Code alone cannot describe trade-offs, assumptions, or constraints. For example, a caching layer may have a function called fetch, which is clear enough, but without documentation, no one knows that it must not be used for sensitive data because it stores results in memory for reuse. Documentation adds meaning that naming alone cannot provide. Documentation also reduces errors. Without it, developers may misuse functions, pass the wrong types of data, or make assumptions that break the system. A function that accepts dates may expect them in UTC, But if that detail is undocumented, someone may pass local times and cause subtle bugs. A line in the documentation stating all timestamps must be UTC prevents such mistakes. The cost of writing it is low compared to the cost of debugging without it. Another important role of documentation is explaining boundaries. Large systems have modules that interact with one another. Documentation defines what each module does and what it does not do. Without this clarity, developers may extend modules in ways that break assumptions. A data processing module may be designed to handle validation only, but without documentation, another developer may add business logic into it. Over time, the module bloats and becomes unmanageable. A clear note in the documentation: this module validates input only. It does not apply business rules, keeps the system clean. Boundaries matter, and documentation enforces them. Documentation does not need to be heavy or formal to be effective. A simple README file can explain the purpose of a project, how to set it up, and how to run tests. Inline comments can explain non-obvious parts of code. A short design document can describe the reasoning behind architecture decisions. These small efforts create huge value. They turn a private system into a shared one, accessible to anyone who reads. Documentation is not about writing long manuals. It is about writing enough to make the code usable and understandable. Even error messages are a form of documentation. A vague message like error 400 tells the user nothing. A clear message like missing required parameter, user_ID, explains what went wrong and how to fix it. This saves time for the person encountering the error, whether they are a user or another developer. In this way, documentation is built into the program itself. Every explanation reduces confusion, and every vague message adds to it. Historical context is another area where documentation shines. Many systems evolve over years, with layers of decisions stacked on top of one another. Without documentation, later developers cannot tell which decisions were deliberate and which were accidents. They may remove something that looks unnecessary, but actually serves a hidden purpose. A short note like this check prevents a known bug in version 2 of the client, prevents such mistakes. Documentation records history so that future developers do not repeat past errors. Think about large organizations that depend on legacy code. Often the biggest challenge is not that the code is old, but that it lacks documentation. Teams spend weeks reverse engineering behavior just to make small changes. If the original authors had documented their reasoning and structure, the same work would take hours. The code still runs, but without documentation, it is a black box. With documentation, it becomes a tool that can be extended and maintained. Developers often underestimate how much they forget their own work. You may believe that a function you wrote is too simple to need documentation. Later, even you struggle to recall why it is written that way. Multiply that by thousands of functions in a large system, and the problem becomes obvious. Documentation saves time and reduces frustration, not by making code perfect, but by making it understandable. Code without docs forces readers to solve puzzles. Code with docs invites them to use, extend, and trust the system. When you first start writing code, it feels like problems can always be solved by being clever. If a function grows messy, you can wrap it in another function. If a module becomes confusing, you can create an abstraction. If a system becomes hard to configure, you can move the settings into a file or a service. Each step feels like progress, as if you have reduced the complexity, but the truth is that complexity never disappears. You can only move it around. You can hide it behind abstractions, push it into configuration, or split it into separate services, but it remains in the system. Trying to outsmart complexity does not erase it. It only changes where you encounter it. Take a common example of database access. At first, you may write SQL queries directly in your code. Over time, the queries multiply, and you decide to use an ORM to simplify things. Now you can fetch objects with methods instead of writing raw SQL. It feels cleaner, but the complexity of SQL still exists. It is now buried inside the ORM. When something goes wrong, such as a query running slowly or behaving unexpectedly, you must look past the abstraction and deal with SQL again. The ORM did not eliminate the complexity of relational databases, It only moved the responsibility from your application code to the ORM's internals. When leaks appear, you are forced back into the world you tried to avoid. Configuration is another place where complexity hides. Suppose you have a web service with many options for performance tuning, feature toggling, and connection settings. Hard coding them in code makes maintenance painful, so you move them into configuration files. This feels like you simplified the program, since the code no longer contains these details, but now you have shifted the complexity into another layer. Someone must manage, validate, and document the configuration. Mistyped values or missing options cause failures. Instead of debugging code, you are debugging configuration. You did not escape complexity, you relocated it. Microservices illustrate this principle at scale. A monolith may become too large to understand, so you break it into smaller services. Each service is easier to grasp in isolation, but the complexity of the whole system grows. Now you must manage inter-service communication, network reliability, distributed transactions, and versioning across services. You solved one kind of complexity by introducing another. The monolith had tangled code, while the microservices have tangled interactions. You chose the form of complexity that fits your needs, but you did not make it vanish. Even simple abstractions inside code show the same truth. Imagine a utility function that wraps error handling. You create it to avoid repeating try-catch blocks everywhere. At first it feels cleaner, but later, someone unfamiliar with the helper must read both the function and the original logic to understand how errors are handled. They must trace through another layer. The complexity of error handling was not removed. It was only placed in a new container. If the abstraction is too generic, it may even add confusion by hiding important details. Frameworks provide another example. A framework gives you a structure, so you do not have to write everything from scratch. But the complexity of building applications does not vanish. It shifts into the framework's conventions, lifecycle, and hidden mechanisms. If you follow the happy path, it feels simple. As soon as you need to step outside of it, you face the full complexity of both your problem and the framework itself. The framework can even make things harder because it adds rules and constraints you must follow. The complexity is still there, waiting behind the curtain. Consider scaling a system. At 10 users, you can manage with a single server and a simple database. At 10,000 users, you add load balancers, caches, and sharding. Each step manages one problem, but introduces new ones. Load balancers need health checks and failover rules. Caches need invalidation strategies. Sharding requires careful key design and query changes. You did not reduce the complexity of handling scale. You transformed it into infrastructure problems. Each piece you add solves one challenge, but carries its own rules and risks. This principle also applies to user interfaces. You may design a simple front end that hides the details of the back end. To the user, it looks clean and intuitive, but under the surface, the complexity is still there. The interface must handle state, synchronize with the server, and reconcile errors when things go wrong. The user sees simplicity, but the developers maintain a more complex system behind it. Hiding complexity does not remove it. It only changes who bears the burden. Security provides some of the clearest examples. A system may offer single sign-on to simplify login for users. From the outside, it feels easier, but internally the system must manage tokens, certificates, expiration, and trust relationships. The complexity of authentication did not disappear. It became concentrated in the integration. If you misunderstand how it works, you may introduce vulnerabilities. What feels like simplicity for the user is often heavy complexity for developers and operators. Documentation and training show the human side of this issue. A developer may create a clever abstraction that hides dozens of details. To them it feels elegant. But the next developer must learn not only the original problem, but also the new abstraction. The mental load increases. Complexity shifted from runtime to learning curve. Instead of facing it while writing code, someone faces it while trying to understand code. Either way, the complexity is paid for. The idea that complexity cannot be outsmarted is humbling. It means that every design decision trades one form of difficulty for another. You choose between a large monolith or many microservices. You choose between raw SQL or an ORM. You choose between hard coding settings or managing configurations. Each choice has costs. Pretending that one path eliminates complexity is a trap. The best you can do is decide where the complexity belongs and who should manage it. Some complexities are worth hiding because they do not need to be exposed everywhere. Abstractions can create boundaries that localize problems. A database driver hides protocol details, so every developer does not need to know them. A configuration file hides environment differences, so the code base stays consistent. But even then, the complexity is not gone. It lives in the driver or the configuration system, waiting to be understood by those who maintain it. The choice to hide complexity works only if you are prepared to deal with it when the time comes. A useful way to think about this is debt. Every abstraction or shift of complexity is like borrowing against the future. You gain simplicity in one place now, but someone must pay the cost of dealing with the hidden details later. If the abstraction is well designed, the debt is manageable. If it is sloppy, the debt grows, and the system becomes fragile. This is why seasoned developers do not chase cleverness. They recognize that hiding complexity without discipline only makes it harder to handle later. Software systems are full of trade-offs. You cannot outsmart them into being simple. Every solution carries hidden weight. Understanding this helps you design more responsibly. You stop asking how to eliminate complexity and start asking where it belongs. You think about who will face it and when. That perspective makes the difference between a system that bends under pressure and one that grows with it. Complexity is not the enemy to be defeated. It is the constant that must be managed. When developers work with cloud services, it is easy to believe hardware is limitless. You can spin up servers in minutes, scale databases with a command, and store terabytes without ever touching a physical disk. The illusion of infinity is strong, but underneath the dashboards and APIs, software still runs on hardware, and hardware follows the laws of physics. Cloud servers are not infinite. They are just someone else's computers, subject to the same constraints of bandwidth, memory, storage, and latency that have always shaped computing. The difference is that the limits show up in new places, often in the form of costs or bottlenecks you did not expect. Think about bandwidth. In the cloud, you can move data between systems with ease, but moving a lot of data comes with a price. At small scale, copying gigabytes between services may feel instant and free. At large scale, moving terabytes becomes slow and expensive. Cloud providers charge for outbound bandwidth, and those costs grow quickly. Developers often discover this only after receiving a massive bill. The hardware limit is not only speed, but also money. The network may physically handle the transfer, but your budget may not. What feels limitless in theory becomes painfully finite in practice. Latency is another reminder that physics cannot be ignored. When two services communicate across regions, the data travels through fiber at the speed of light. That speed is fast, but not instantaneous. A round trip between continents takes hundreds of milliseconds. For interactive systems, those delays add up. You can add more servers, but you cannot beat the physics of distance. This is why content delivery networks exist. They bring data closer to users to reduce latency. The software may look flexible, but it bends around the hard limits of time and space. Hardware is not infinite, and speed has ceilings. Memory shows the same principle. At a smaller scale, a virtual machine or container may let you specify as much RAM as you like, but when your program exceeds that memory, it crashes or slows due to swapping. The cloud does not remove the fact that memory is finite. It just makes it easier to forget until the failure happens. Developers sometimes load entire datasets into memory because it feels convenient. On small sets, this works fine. On larger sets, the program grinds to a halt. The hardware limit reminds you that design choices must respect reality. Storage has similar constraints. Cloud services promise virtually unlimited storage, but limits emerge in throughput and access patterns. Writing millions of small files may overwhelm metadata operations. Reading large amounts of data at once may hit I/O ceilings. Even if storage space itself is vast, the speed of accessing it is not. Hard drives, SSDs, and distributed storage systems all have bottlenecks. The cloud hides the hardware, but it cannot remove its characteristics. Developers who assume infinite capacity are surprised when performance falls apart under real workloads. Compute power also reveals hard edges. A function running in a serverless environment may scale to thousands of instances, but each instance still has time and resource limits. Long-running tasks may time out. Heavy computations may exceed CPU quotas. Parallelism can spread work across many cores, but not every problem divides neatly. Some algorithms remain limited by sequential steps. Moore's law once gave steady improvements in performance, but those gains have slowed. Adding more cores helps, but not without introducing complexity in concurrency and synchronization. Software cannot outpace the boundaries of hardware. Costs act as another form of limit. Cloud platforms make scaling simple, but every extra server, request or byte has a price. For startups, the bill may grow faster than the user base. A feature that seems harmless at low traffic may become unsustainable at high traffic because of cost. For example, logging every request in detail may be fine for 1,000 users. At 1 million users, the storage and analysis costs may explode. The system still works, but the financial hardware, your budget runs out. This is another way reality enforces limits. Energy consumption ties software back to physics as well. Data centers consume enormous power to keep servers running and cool. The cloud abstracts this away, but the demand is real. Providers build facilities near cheap energy sources and invest in efficiency because the limits of energy and heat are unavoidable. For developers, this surfaces in throttling or quotas. Providers cap usage to protect their infrastructure. You cannot run endless workloads without hitting a ceiling somewhere. The physical cost of computation always comes due. These limits influence design choices. A developer building a video streaming service must compress data to reduce bandwidth costs. They must cache content near users to reduce latency. They must choose encoding formats that balance quality with file size. Every decision acknowledges that hardware is finite. Without those constraints, the service would collapse under its own weight. The illusion of infinity vanishes when the first wave of users pushes the system to its edges. Another example is machine learning. Training large models requires vast amounts of compute, memory, and storage. Researchers often hit GPU memory limits that force them to design more efficient architectures or distribute training across multiple machines. Even in the cloud, where you can rent powerful hardware, availability and cost create limits. You may want 1,000 GPUs, but you can only afford 10. The work must adapt to hardware constraints, not the other way around. Physics and economics shape what is possible. Developers sometimes believe optimization is unnecessary because hardware is cheap. This mindset works at small scale, but at large scale, inefficiency compounds. A query that takes 1 second for 10 users may take hours for millions. Adding more servers may delay the problem, but it cannot remove it. The real solution is designing with hardware in mind, efficient queries, proper indexing, caching, and thoughtful architecture. Software always inherits the limits of the machines it runs on. Even mobile devices remind us of these truths. Apps built without regard for battery, memory, or network usage may run fine in testing, but frustrate users in real life. A phone's hardware is more obviously finite than the cloud, but the principle is the same. Developers must design within constraints. Ignoring them leads to crashes, slowdowns, and poor user experiences. Whether on a phone or in a data center, hardware sets the boundaries. The illusion of infinity in cloud computing comes from convenience. Provisioning feels effortless, scaling looks automatic, and storage seems endless. But every one of those abstractions sits on top of physical servers, disks, and cables. Someone manages them, someone pays for them, and someone hits their limits. Software may feel abstract, but it cannot escape the fact that it runs on machines bound by physics. The sooner developers accept that hardware is not infinite, the better they can design systems that work within those limits instead of being broken by them. When developers talk about performance, the conversation often centers on speed. Everyone wants their code to run faster, handle more requests, and use fewer resources. But performance is never free. Every optimization comes with a price. Making something faster usually makes it less flexible, harder to read, or less safe. Performance is always about trade-offs. The real challenge is not how to optimize, but how to balance speed with other qualities that matter just as much. Take the example of caching. Caching is one of the most common ways to improve performance. Instead of recalculating or refetching data, you store the result and return it quickly next time. The trade-off is freshness. Cached data can become stale, and systems must handle invalidation. In practice, invalidation is one of the hardest problems in computer science. You gain speed at the cost of complexity and potential correctness. Developers who only see the speed improvement miss the burden of maintaining consistency. The cache makes the system fast but less flexible and less predictable. Another example is memory management. You can write code in a low-level language like C and manage memory directly. This gives you high performance and fine control, but it comes at the price of safety. A single mistake can cause memory leaks, buffer overflows, or crashes. Languages with garbage collection, like Java or Python, trade raw speed for safety and developer productivity. Garbage collection adds overhead, but it reduces the risk of errors. Choosing performance here means accepting higher risk and more complexity in exchange for speed. Data structures also reveal the trade-offs. A linked list allows fast insertion and deletion, but slow random access. An array allows fast indexing, but expensive resizing. A hash map provides quick lookups on average, but it consumes more memory and can degrade in performance with poor hashing. Each choice optimizes one aspect while weakening another. There is no universal structure that is both the fastest and the safest in all scenarios. The decision depends on which trade-offs you are willing to accept. Concurrency shows another layer of trade-offs. You can parallelize tasks to use multiple cores and finish faster, but parallelism introduces race conditions, synchronization overhead, and non-deterministic behavior. Debugging becomes harder. Logs may appear in different orders, and errors may vanish when you try to reproduce them. The system runs faster, but it becomes less predictable and less readable. The gain in performance costs you simplicity and safety. Sometimes that cost is worth it. Other times it is not. Even compilers reflect these trade-offs. You can optimize for speed, for size, or for debugging. An executable compiled with maximum speed optimizations runs faster but is harder to debug. Variable names disappear, instructions are reordered, and stepping through code makes little sense. Optimizing for size may save memory, but reduce runtime performance. The compiler cannot give you all benefits at once. It forces you to choose the trade-off that matches your priorities. Database indexing is another case where optimization has a cost. Adding an index speeds up queries that use it, but it slows down writes, because each new row must update the index. With too many indexes, inserts and updates grind to a halt. Optimizing for read speed sacrifices write speed. Developers must weigh which operations matter more. An e-commerce site may optimize reads for product browsing, while a logging system may optimize writes to handle high ingestion rates. The choice reflects a balance, not a universal answer. Readability often suffers when performance takes priority. Consider a tight loop optimized for speed. You might unroll it manually or replace clear code with bitwise operations. The result runs faster, but the logic becomes harder to understand. The next developer may struggle to maintain it. If they introduce a bug, the cost of debugging outweighs the performance gain. Clean, readable code is slower in execution but faster in comprehension. The trade-off is between machine speed and human speed. Safety can also be compromised by premature optimization. Developers sometimes inline functions, skip validation checks, or remove error handling to reduce overhead. The program runs faster, but it becomes fragile. If unexpected input arrives, the system may crash or behave unpredictably. What was gained in milliseconds may be lost in reliability. Systems that prioritize safety over raw performance often survive longer and scale better, because crashes and security flaws cost far more than slow execution. Network systems highlight the same pattern. Compression reduces bandwidth usage and speeds up transfers over slow networks, but it increases CPU load for compressing and decompressing. Encryption secures communication but adds latency. You cannot have infinite speed, full safety, and zero cost all at once. Each choice optimizes one area while weakening another. Designing distributed systems always involves deciding which limits to accept. User interfaces provide another example. A developer may prefetch data to make screens load instantly, but prefetching consumes bandwidth and battery, which may harm mobile users. Lazy loading saves resources but makes screens slower when first opened. The trade-off is between perceived performance and resource efficiency. You optimize one side, and you pay on the other. Even languages themselves reflect performance trade-offs. Python emphasizes readability and developer speed. It sacrifices raw execution speed compared to C. C offers high performance but at the cost of manual memory management and steeper learning curves. Go chooses simplicity and concurrency, trading some performance for easier scaling. Rust focuses on memory safety and high speed, but with stricter rules that slow development. No language gives everything. Each balances performance, safety, and usability differently. In practice, performance work often follows a cycle. Developers build something clear and correct first. Then they measure where the real bottlenecks are. Only then do they optimize. This approach acknowledges that optimization always has a price. By waiting until you see real problems, you avoid paying costs where they are not needed. Premature optimization can lead to unreadable code that solves a problem you never had. Smart developers focus on clarity first, then pay for performance only where it matters. Trade-offs appear even in hardware. CPUs can be designed for higher clock speeds, but this increases power consumption and heat. GPUs can provide massive parallelism, but are inefficient for sequential tasks. Solid-state drives are fast but wear out after many writes. Mechanical drives are cheaper with higher capacity but much slower. Every layer of computing reflects choices about what to optimize and what to sacrifice. Software that ignores these trade-offs often fails when real-world constraints appear. An example from the real world shows the cost clearly. A company builds a recommendation engine and optimizes it heavily for speed. It returns results instantly, but the code is so complex that only one engineer understands it. When that engineer leaves, the system becomes a liability. Another team builds a slower version that is easy to maintain and extend. It runs with higher latency, but it survives longer because the cost of maintenance is lower. The trade-off was not about raw performance alone, but about balancing speed with sustainability. Performance is about trade-offs because computing is about limits. Time, space, safety, readability, and maintainability all compete. Improving one usually means weakening another. The art of programming is not finding the fastest solution in isolation. It is finding the right balance for the problem, the team, and the system as a whole. Optimization always has a price, and the real skill lies in deciding when it is worth paying. When you begin a software project, the first thing you are often given is a specification. It may be a document, a list of features, or a set of user stories. It feels like the blueprint for what you must build. You may think that if you follow it carefully, the work will be complete and the product will be finished. But this is not how software works. The spec will change, requirements evolve because businesses shift, users discover new needs, and technology reveals new possibilities. Code is not a monument carved in stone, it is a living organism that adapts over time. Imagine a team building an online ticketing system. The initial spec says users must be able to buy tickets and receive email confirmations. The team builds exactly that. But once users start buying tickets, complaints arrive. They want mobile notifications, not just emails. The business wants to add discount codes. Regulators ask for tax information on receipts. Each change feels small, but together they reshape the system. The original spec was not wrong, but it was incomplete. No one can anticipate every requirement before real users interact with the product. The spec must evolve, and the code must evolve with it. This is why rigid designs often fail. A developer who believes the spec is final may build tightly coupled systems that resist change. They assume the fields, endpoints, and workflows will remain the same forever. When new requirements arrive, the system bends awkwardly or breaks entirely. On the other hand, A developer who expects change designs for flexibility, they leave room for extensions, use modular structures, and avoid assumptions that lock the system into one shape. They know the spec is just a snapshot of current thinking, not the final truth. You can see this most clearly in user interfaces. An early design may call for a simple list of items. The team implements it. Then users ask for sorting, filtering, and search. Later, the business wants recommendations displayed next to items. What began as a static list becomes a complex interface. If the developers built the list as a fixed page, they must rewrite large parts of the code. If they built it as reusable components, they can adapt more easily. The difference is not in predicting the exact changes, but in accepting that changes will come. APIs are another area where the spec will change. You may publish an endpoint with certain fields. Months later, new data becomes necessary, and clients want it added, or a field you thought was optional turns out to be critical. The API must adjust. If you designed it with versioning and backward compatibility in mind, you can evolve it smoothly. If you assumed the spec would stay fixed, every change becomes painful. APIs, like code, live longer than their initial design. They reflect evolving business needs and cannot remain static. Even performance requirements evolve. A spec may begin with simple expectations, handle a few hundred users. After launch, demand grows, and now the system must handle thousands or millions. What was acceptable yesterday is inadequate today. The system must scale, and that often means redesigning parts of it. Developers who believed the initial numbers were permanent are caught off guard. Those who treated them as temporary markers are ready to adjust. The living nature of code means performance targets are not fixed milestones, but moving goals. Security also drives changes. A spec written at the start of a project may meet the known standards of the time, but as threats evolve, new requirements appear. A system that once allowed simple passwords must now enforce stronger rules. A service that once logged data freely must now comply with privacy regulations. Developers cannot cling to the old spec because attackers and regulators do not respect it. Security forces code to change, often in ways no one imagined when the project began. The culture of software development reflects this reality. Agile methods exist because rigid specs fail to capture the dynamic nature of software. Instead of treating the spec as final, Agile teams treat it as a guide. They expect it to change as users give feedback and as priorities shift. Each sprint delivers something real, and each release teaches something new. The cycle of building, testing, and revising accepts that requirements are not stable. Code is not finished, but constantly shaped. Legacy systems show how specs evolve over decades. Many companies run software written with requirements that are now obsolete. Banking systems, for example, were designed for batch processing in a world before online transactions. Over time, they were adapted to support ATMs, online banking, and mobile apps. The original specs never mentioned these things, but the code had to grow to support them. Entire industries rely on systems that outlived their initial requirements. Code written for one world ends up serving another. Even small projects prove the point. A developer may build a personal tool with a narrow spec, parse a file, and display results. Later, they want it to handle more file types, export data, or share results with others. The code must change. What began as a weekend project evolves into something larger. The spec changes not because the original was wrong, but because the developer's needs changed. This mirrors the evolution of all software, from personal scripts to global platforms. Sometimes the spec changes because reality does not match assumptions. A team may design for ideal users who follow the rules. After release, they discover users make mistakes, input bad data, or misuse features. The system must adapt to handle errors gracefully. Error handling, validation, and logging often grow far beyond the original spec. The real world shapes requirements more than documents do. Developers who expect perfection from the start are disappointed. Those who expect surprises are prepared. The truth is that no spec can capture the future. Businesses pivot, users change, regulations evolve, and technology advances. Code that cannot adapt becomes obsolete. Code that can adapt continues to serve. This is why experienced developers talk about maintainability as much as functionality. A program is never finished in the same sense a building might be. It is closer to a living organism that grows, heals, and adapts to survive in its environment. When you write code, you are not completing a project once and for all. You are creating a foundation that others will change, including yourself. The spec is not a boundary, but a starting point. Expect it to evolve. Expect to revisit decisions. Expect the code to change. That mindset makes the difference between systems that fail under the weight of change and systems that thrive with it. When developers think about bugs, they usually see them as mistakes. A bug is a flaw in the code, something that does not behave as intended. The natural instinct is to fix it as soon as possible, but the reality of software use is more complicated. Sometimes what looks like a bug to the developer becomes a feature for the user. People adapt to the behavior of software. Even when that behavior was never planned, they build their habits and workflows around it. Fixing the bug may not feel like an improvement. Instead, it may feel like a loss. Bugs can be features, and treating them only as errors can create more problems than leaving them in place. Consider a word processor that accidentally auto-saves a backup copy every time the user closes a document, even if they disabled the autosave option. From a developer's view, this is a bug. The program ignores the user's choice, but for some users, this behavior saves them from lost work when they forget to enable saving. They may come to rely on those extra copies. If the development team fixes the bug by making the program respect the setting, those users suddenly lose the safety net they had grown accustomed to. They see the fix as a regression, not an improvement. Another classic example comes from video games. Many famous techniques in games started as unintended behaviors. In the game Street Fighter II, players discovered that quickly cancelling one move into another created combos. The developers had not planned this, but players loved it. Instead of fixing it, later versions of the game embraced combos as a core mechanic. What began as a bug turned into one of the most important features of the genre. The same story repeats across gaming. Glitches become strategies, and fixes sometimes anger players who relied on them. In business software, bugs can create unofficial shortcuts. Suppose an accounting system has a flaw where entering 0 in a field skips certain validation checks. Users may discover this and start using it as a quick way to bypass restrictions they find cumbersome. For the developers, this is a clear bug, but for users, it becomes a hidden feature that improves their workflow. If the team patches it, users may complain that their jobs just got harder. The software behaves more correctly, but it feels worse to those who adapted to the flaw. Web browsers also provide many examples. Early versions of HTML had vague specifications, and browsers implemented them inconsistently. Developers of websites discovered ways to rely on quirks of specific browsers. A page might only render properly because of a bug in how the browser handled tags. Later, when browser vendors fixed those bugs, many sites broke. To avoid mass disruption, browsers introduced quirks mode to preserve old behavior. This compromise shows the power of bugs that become features. Millions of websites depended on unintended behaviors, so vendors had to keep supporting them long after the bugs were understood. Sometimes bugs create behaviors that expand the usefulness of a product beyond its original design. An example is spreadsheet software like Excel. Certain functions produced results that were technically incorrect but gave users flexibility in handling data. Instead of fixing them outright, the software maintained compatibility because too many people relied on the wrong results for their workflows. Correcting the bug would have broken entire businesses built on those spreadsheets. The safe path was to treat the bug as part of the program's behavior. Operating systems face similar dilemmas. Applications often rely on undocumented behavior, which may originate from bugs. Developers of those applications build around the quirks because they exist in practice, even if they were never intended. If a new version of the operating system removes or fixes that quirk, applications may crash. Users blame the operating system, not the application. To preserve compatibility, system vendors often carry old bugs forward for decades. Windows, for example, maintains many strange behaviors simply because fixing them would break too much existing software. The tension between correctness and user expectations is at the heart of this issue. Developers want code that matches the spec, that behaves logically and consistently. Users want systems that match their habits, even if those habits grew from mistakes. From the user's perspective, the software's actual behavior, not the intended one, defines what the program is. If the code says one thing but reality says another, reality wins. Fixing a bug changes reality, and change is disruptive. This does not mean every bug should remain unfixed. Some cause crashes, data loss, or security risks. Those must be addressed, even if some users resist. But many bugs are less clear. They may create odd behavior that is harmless or even useful. In those cases, fixing them requires careful thought. Developers must ask who is relying on the behavior, how they are using it, and what the impact will be if it disappears. Sometimes the safest path is to leave the bug alone, or to fix it only after providing an alternative feature that supports the same use case. Communication plays a key role. If developers decide to fix a bug that users depend on, they should explain why and give advance notice. They should provide migration guides or new features to replace the old behavior. Sudden fixes with no warning feel like betrayal to users. A relationship of trust depends on recognizing that bugs once adopted become part of the product's identity. Removing them without care damages that trust. Developers also learn from these situations. When a bug becomes a feature, it shows that users wanted something the original design did not anticipate. The unintended behavior reveals unmet needs. In the case of fighting games, combos showed that players enjoyed chaining moves. In business software, bypassing validation showed that users wanted more flexibility. Instead of fighting these patterns, smart developers integrate them. They turn accidental discoveries into intentional design. Bugs can be signals about what users value. The idea that bugs can be features challenges the way we think about software quality. It is not just about matching the spec. It is about meeting user expectations, even when those expectations are shaped by mistakes. This creates tension between technical purity and practical reality. Developers may feel frustration when their clean fix is received as a downgrade, but this tension is part of the craft. Software is not just logic written in code, it is a tool that people shape to their own purposes. Once shaped, it resists being reshaped, even in the name of correctness. For anyone building systems, the lesson is to treat bugs with caution. They are not always simple errors to erase. They may have become dependencies, features in disguise, or signs of deeper needs. Understanding this changes how you approach maintenance. It reminds you that users decide what is useful, not just specifications or code. What begins as a flaw can grow into the heart of a workflow, and fixing it without care can cause more harm than leaving it alone. When you write code, you often think in terms of clear cause and effect. A function takes an input, performs an operation, and produces an output. You test it, confirm the result, and feel confident that you understand how it behaves. But when software systems grow and begin to interact with each other, the story changes. The parts combine in ways no single programmer designed or predicted. Unexpected patterns appear, and the system takes on a life of its own. This is emergent behavior, and it is real. It is not a mistake in the sense of broken code. It is the natural result of complexity. A simple example is traffic on a website. One developer builds the front end, another manages the database, and a third sets up caching. Each part works as intended. But under heavy load, the cache fills, the database slows, and the front end retries requests. The retries multiply the pressure on the back end, which slows further. Soon the system collapses, not because any component failed on its own, but because their interactions produced a feedback loop. No one wrote code that said crash under load. The behavior emerged from the system as a whole. Distributed systems show this even more clearly. Consider microservices that depend on each other. Service A calls service B, which calls service C. Each has its own retry logic to handle temporary failures. If service C slows down, service B retries, and so does service A. Instead of easing the problem, retries amplify the traffic. What began as a small slowdown cascades into a flood of requests that overwhelms all three services. The developers who wrote each retry mechanism thought they were improving reliability, Together they created instability. The emergent behavior was not designed, but it was real and damaging. Another example comes from machine learning systems. A developer trains a model to maximize user engagement. The model tries different strategies and discovers that showing controversial or extreme content keeps users active longer. No one told the system to push harmful material. The programmers only told it to maximize a metric, but the combination of algorithms, user behavior, and feedback loops produced an outcome that no one planned. The emergent behavior reflects the interaction between software and humans, not a single line of code. Even simple rules can produce surprising results. Cellular automata, like Conway's Game of Life, use basic conditions for how cells live or die. Yet when applied across a grid, these rules generate complex patterns that look like organisms moving, reproducing, and evolving. No one programmed the shapes directly. They emerged from the interactions of simple rules. In real systems, the rules are far more complicated, and the patterns more unpredictable. The principle remains the same. Complexity arises from interactions, not individual parts. Emergent behavior is not always negative. Sometimes it creates valuable features. For example, early peer-to-peer networks were designed for file sharing, but the same architecture allowed them to be used for distributed computing, load balancing, and resilience against single points of failure. The benefits emerged from the way nodes interacted, not from deliberate design. Similarly, developers of online games discovered communities forming complex economies, with players creating markets, currencies, and social systems beyond what the designers imagined. These emergent behaviors added richness to the game, even if they were never planned. However, emergent behavior often surprises teams because testing individual parts does not reveal it. Unit tests pass. Integration tests pass. Only when the system runs at scale, under real conditions, do the unexpected patterns appear. This is why bugs in large systems can be so hard to reproduce. The problem is not in one function but in how functions interact under certain conditions. Debugging then becomes a matter of understanding the system as a whole, not just its parts. Feedback loops are one of the most common causes of emergent behavior. A small action triggers a response that magnifies the original action. This can spiral out of control, as in retry storms, or it can stabilize a system, as in load balancers distributing traffic. Whether the outcome is harmful or helpful depends on the balance of forces. Programmers may not even be aware that a feedback loop exists until it reveals itself in production. By then, the emergent behavior is entrenched. Human interaction with systems creates another layer of unpredictability. Users often find ways to exploit features in ways developers never anticipated. A classic case is when users discover loopholes in reward systems. For instance, a fitness app may reward points for activity, so users strap their phones to fans or shake them to simulate steps. The code works as written, but the outcome defies the original goal. Users interacting with the system create emergent patterns that undermine the design. This shows that emergent behavior is not just technical but also social. Financial systems offer many striking examples. Automated trading algorithms operate according to rules designed by programmers. Each one may work fine alone, but when thousands of algorithms interact in the market, they sometimes create flash crashes, where prices plunge and recover in seconds. No single programmer designed this outcome. It emerges from the interactions of many independent systems competing and reacting at high speed. The financial world has had to adapt to these realities, not by eliminating them but by building safeguards that account for emergent behavior. Managing emergent behavior requires a mindset shift. You cannot assume that controlling individual parts will control the whole. You must observe how parts interact, test at scale, and expect the unexpected. Chaos engineering is one method that embraces this idea. Teams deliberately break parts of their systems in controlled ways to see how they respond. The goal is to expose emergent failures before they happen in the real world. By treating the system as a living organism rather than a static machine, developers learn to anticipate the unpredictable. Emergent behavior also raises questions of responsibility. When a system produces harmful outcomes no one explicitly coded, who is accountable? The developers who wrote the rules, the managers who set the goals, or the users who shaped the patterns? In practice, responsibility is shared. Recognizing that emergent behavior is real does not excuse harm, but emphasizes the need to design with awareness of complexity. Setting goals, monitoring outcomes, and adapting to unintended consequences are all part of building resilient systems. The reality is that emergent behavior cannot be eliminated. It is the natural result of complexity and interaction. The more parts a system has, the more likely it is that unexpected outcomes will arise. Programmers cannot predict everything. They can only design with humility, knowing that surprises will occur. Some surprises will delight users, creating value no one expected. Others will cause failures, outages, or even crises. The challenge is not to prevent emergence, but to recognize it, manage it, and adapt to it when it happens. When people imagine the systems that power banks, airlines, hospitals, and governments, they often picture clean, modern software built with the latest tools. The reality is very different. Most critical systems are old, patched, and messy. They were written decades ago, often in languages many developers no longer use, and they have been maintained with layer upon layer of fixes. Yet these systems continue to run because replacing them is too risky or too expensive. The world runs on duct tape, not perfection. Legacy code is not a rare exception. It is the foundation of much of modern life. Take the financial sector as an example. Many banks still run core systems written in COBOL, a language first introduced in the late 1950s. These systems handle account balances, transactions, and interest calculations. They are reliable in the sense that they keep working, but the code is sprawling and hard to understand. Over the years, developers added patches to adapt to new regulations, new products, and new technologies. Instead of rewriting the system, banks kept building on top of what already worked. Today, many of those who understand COBOL are retired or close to retirement, yet the code continues to run because moving billions of dollars to a new platform is a risk no bank wants to take. Airlines provide another case. Reservation systems were built decades ago, long before the internet. They were designed to handle phone bookings and printed tickets, not online searches from millions of users. As travel expanded, these systems were patched to connect with websites, mobile apps, and partner airlines. Each patch added complexity, but the core remained. When these systems fail, flights around the world get cancelled, not because the planes are broken, but because the software that coordinates passengers is overwhelmed. Legacy code in these systems holds together the global travel network. Healthcare is also full of legacy systems. Hospitals often run medical record systems that are decades old. These systems may be slow and clunky, with interfaces that look outdated, but they contain vital patient data. Migrating to new software risks data loss, errors, and downtime in environments where mistakes can cost lives. So hospitals continue using what they have, adding layers of integration to connect with newer tools like digital imaging, mobile apps, or national health databases. The result is a mix of old and new, stitched together in ways that work but are far from elegant. Governments face the same problem. Tax systems, benefit programs, and defense infrastructure often depend on code written long ago. These systems were built for smaller populations, simpler rules, and slower networks. Over time, laws and regulations changed, and developers bolted new logic onto the old base. Today, the systems are labyrinths of patches. They work, but only because teams of specialists keep them alive. Replacing them would require years of work, billions of dollars, and political will that rarely exists. So they endure, running the basic functions of society behind the scenes. Legacy code survives because it works. It may not be clean or modern, but it handles real tasks that matter. Companies and institutions prefer the certainty of messy code that runs to the risk of rewriting everything. Rewrites often fail. History is full of stories where organizations tried to replace legacy systems, spent enormous sums, and ended with nothing usable. Meanwhile, the old system kept running. The fear of failure makes organizations cautious. They would rather live with the imperfections than risk collapse. Developers who work on legacy code often describe it as archaeology. You dig into files that have been touched by dozens of hands over decades. You find comments that no longer match the code, variables with confusing names, and patches on top of patches. You learn not just programming but history, why certain decisions were made, what crises shaped the system, and how compromises piled up. Debugging a legacy system is often less about logic and more about understanding the story behind the code. The messy nature of legacy code comes from survival. Every time a new requirement appears, the system adapts, a patch is added, a workaround is built, and the system continues. Over time, this creates complexity that no one would design from scratch, but it also shows resilience. Legacy systems are alive because they have been able to bend and stretch. They may be ugly, but they are durable. In many ways, this makes them stronger than new systems that have yet to face decades of change. Working with legacy code teaches humility. It shows that perfection is not necessary for success. Systems that look fragile often hold together because people keep them alive. Developers learn to balance improvement with stability. They cannot always rewrite messy parts, but they can document, test, and refactor where possible. The goal is not to create a perfect system, but to keep a critical one running safely. This is a different mindset from building something new. It values pragmatism over purity. One striking aspect of legacy code is how invisible it is. Users rarely see it, yet they depend on it every day. When you withdraw money from an ATM, book a flight, or file taxes, you interact with systems powered by decades-old code. The modern interface hides the age of the back-end. New apps and services often connect to legacy systems through APIs or integration layers. The shiny surface masks the duct tape underneath. But if the old code fails, the new layers collapse with it. Sometimes organizations attempt to replace legacy systems incrementally. They wrap old code in services, build new modules alongside, and gradually shift functionality. This approach can work, but it requires discipline and patience. More often, organizations accept that legacy systems will remain and focus on maintaining them. They invest in training new developers in old languages, writing documentation, and creating monitoring tools. Legacy code may never be replaced, but it can be managed responsibly. The presence of legacy code also shows the importance of maintainability in software design. Code that survives decades is rarely elegant, but it has one quality that matters: it can be changed. Even if the changes are messy, they are possible. Systems that resist change do not last. The duct tape approach, while imperfect, keeps systems flexible enough to adapt. That adaptability is why they are still here. Legacy code is often mocked by developers who prefer working on greenfield projects. But the truth is that legacy systems are where the real impact lies. They handle money, power, health, and security. They matter not because they are beautiful, but because they are essential. Developers who work on them carry responsibility that goes beyond code style or architecture. They maintain the fragile but functional foundations of the modern world. The idea that the world runs on duct tape, not perfection, may seem discouraging, but it is a reminder that software is not judged by elegance alone. It is judged by whether it continues to serve real needs. Legacy code, with all its flaws, has proven itself by surviving. It runs the world not because it is perfect, but because it works, and because replacing it is harder than keeping it alive. When you first write code, you usually believe you understand how the system behaves. You picture the flow of logic, the data moving through functions, and the outcomes you expect. Then a bug appears. Something does not work as you imagined. At first it feels like a failure, but if you look closely, every bug is a lesson. Debugging is not just fixing mistakes. It is learning how the system actually behaves compared to how you thought it behaved. Each bug you chase pulls back the curtain on reality, showing details you overlooked, assumptions you made, and interactions you did not see. Take a simple example. You write a function to calculate totals from a list of numbers. You assume the inputs are always integers. Later, a bug report arrives, saying the totals are wrong. You investigate and discover that sometimes the inputs include strings like 5 inches instead of integers. The code concatenates instead of adding. The bug teaches you that your assumption about the input was wrong. You thought the system passed only integers, but in practice it allowed strings. Debugging corrected not just the code, but your understanding of the data. This pattern repeats at every level of development. A network service times out, and you learn that latency spikes under load are higher than you expected. A database query slows down, and you realize your index is not being used the way you thought. A UI crashes, and you discover that users interact with it in ways you never tested. Each bug forces you to compare mental models with reality. The gap between them is where the bug lives. Closing that gap is what debugging does. Debugging also teaches you about the tools you use. Many developers learn the inner workings of frameworks, libraries, and operating systems only when things go wrong. You might assume your web framework handles session storage in memory, but a bug reveals it stores sessions in the database by default. You might believe your logging library writes to disk synchronously, but a bug shows it buffers logs in memory first. These discoveries often come through hours of debugging. The tools you use are full of details you do not fully know. Bugs expose those details, sometimes painfully, but always with lessons. Complex systems magnify this effect. When multiple components interact, your mental model becomes even less accurate. You may think a message queue guarantees order, only to find that retries break the sequence. You may believe an API always returns valid JSON, until you hit a rare edge case where it returns HTML error pages. Each time, the bug is not just an error in code, but a revelation about how the system actually works. Debugging becomes a form of exploration, mapping the unknown territory of your own software. Debugging also reveals how users behave. Developers often assume users will follow intended paths. In practice, users are creative, careless, or simply different from what you imagined. A user might paste 1,000 lines into a text box you assumed would hold a few sentences. A customer might click the same button 10 times in frustration, sending duplicate requests. These behaviors create bugs that expose the gap between design and reality. Debugging them teaches you about real-world use, not just ideal use. Sometimes debugging teaches you lessons beyond software. A bug that surfaces only in production may highlight weaknesses in your testing strategy. You thought your tests covered the system, but they did not cover realistic data volumes or failure modes. The bug is a lesson in process as much as code. It shows you where your practices need improvement. Similarly, a bug caused by unclear documentation reveals the importance of communication. Debugging often shows that software is not just logic, but a reflection of the people, processes, and assumptions that built it. The act of debugging itself develops skill. Beginners often flail, changing code randomly and hoping for results. Over time, you learn discipline. You isolate variables, reproduce problems, and use tools like debuggers, logs, and profilers. Each bug becomes an exercise in methodical thinking. You learn patience because some bugs take hours or days to track down. You learn humility because many bugs come from your own mistakes. Debugging shapes the way you think as a developer. It trains you to be curious rather than defensive, persistent rather than frustrated. Some bugs become turning points. A developer might struggle with concurrency, then face a race condition that forces them to learn about locks, atomic operations, and memory models. Another might struggle with scaling, then debug a performance bug that forces them to understand database indexing. These bugs teach concepts that no tutorial can fully explain. They leave scars and lessons that stick. Debugging transforms abstract ideas into lived experience. Debugging also teaches the limits of control. You may believe you command the system, but bugs remind you that systems are complex and full of surprises. Hardware glitches, network failures, and subtle timing issues can produce behavior no one anticipated. Debugging teaches respect for uncertainty. You stop assuming you know everything, and start building systems with resilience. You add retries, validation, monitoring, and logging, not because you expect perfection, but because debugging taught you that perfection does not exist. Even the feeling of relief after fixing a bug is instructive. You not only restore function but also expand your understanding. You see the system more clearly than before. The code may work now, but the real value is in what you learned about its internals, its users, and your own assumptions. Debugging is never wasted effort, because even when it feels like chasing shadows, it builds knowledge. There is also a collective side to debugging. Teams learn through bugs. A post-mortem on an outage spreads lessons beyond the individual who fixed it. The team learns about hidden dependencies, fragile assumptions, and better practices. Over time, these shared lessons make the team stronger. Debugging then becomes not just a way to fix problems, but a way to grow institutional knowledge. The bugs you face today prepare you for the systems you will build tomorrow. In many ways, debugging is the truest form of programming. Writing code expresses how you think the system should work. Debugging shows you how it actually works. The contrast between intention and reality is where growth happens. Each bug is a teacher, pointing out where your understanding was shallow, where your assumptions were wrong, or where your tools behaved differently than expected. Chasing bugs is chasing truth, and every truth you uncover makes you a better developer. Every software project carries debt. This debt does not involve money, at least not directly, but it creates a cost that must be paid later. Technical debt is the result of shortcuts, compromises, and decisions made under pressure. You cannot avoid it. It is built into the nature of building software. The art is not in pretending you can eliminate it, but in knowing when to refactor and when to let it slide. Think of technical debt like financial debt. Borrowing money lets you move faster today, but you pay interest tomorrow. Cutting a corner in code lets you deliver a feature quickly, but you take on a burden that makes future changes harder. The shortcut saves time in the short term, but creates drag in the long term. Every team faces this trade-off. Sometimes the shortcut is worth it, sometimes it is not. The difficulty lies in deciding which debts to accept and which to pay down. Imagine a startup racing to release its first product. The team writes code quickly, with little time for structure or tests. They know the code is messy, but their priority is survival. If the product fails to launch, clean code does not matter. So they take on debt knowingly, betting that success will give them time to refactor later. In this case, technical debt is not a mistake, but a strategy. The team uses it to buy speed when speed matters most. But if they never return to clean up, the same shortcuts that helped them launch will slow them down. Features will take longer, bugs will multiply, and the system will grow fragile. Now consider a large company with a mature product. The system has been running for years, with layers of patches and workarounds. The debt here is not a deliberate choice, but the accumulation of history. Over time, requirements changed. Developers came and went, and compromises piled up. The company now faces slow builds, tangled dependencies, and brittle code. Unlike the startup, they cannot afford to let it slide forever. Their debt is a drag that threatens stability. For them, the art is choosing where to refactor first, targeting the parts of the system that create the most pain. Not all technical debt is obvious. Some comes from using frameworks or libraries that age poorly. A decision that was sound 5 years ago may become a liability when the framework is abandoned or cannot scale. The debt was invisible until time revealed it. Other debt comes from assumptions that no longer hold. A database schema designed for small amounts of data becomes unworkable at scale. An API built for one use case struggles when expanded. These forms of debt are not about sloppy code, but about the gap between past decisions and present needs. Knowing when to refactor is about balancing risk and reward. If a piece of messy code is stable and rarely touched, it may not be worth the effort to clean up. The debt exists, but its interest rate is low. On the other hand, if developers must constantly work around a bad design, the interest rate is high, and refactoring pays off quickly. Wise teams measure debt not just by how ugly the code looks, but by how much it costs in real productivity. They refactor the parts that slow them down, and accept debt in areas that do not matter. Refactoring itself is not free. It takes time, and it can introduce new bugs. That is why teams often postpone it. But postponement also has costs. The longer debt lingers, the harder it becomes to fix. Systems grow around it, and assumptions harden. Eventually, what was once a small compromise becomes a structural weakness. Some teams learn this only when the system collapses under pressure. A critical bug or a scaling failure forces them to pay down years of neglected debt in a rush. That is the most expensive way to deal with it. Good practices help manage debt before it spirals. Writing tests makes refactoring safer because you can confirm that changes do not break behavior. Code reviews catch some shortcuts before they pile up. Documentation helps future developers understand why decisions were made. These practices do not eliminate debt, but they make it easier to live with and easier to pay back. They lower the interest rate. An example from the real world is the payments industry. Systems that process transactions often carry huge amounts of technical debt. Regulations change, new payment methods appear, and fraud tactics evolve. Developers patch systems to adapt, layering fixes on top of fixes. Over time, the code becomes messy. Yet these systems continue to run because the cost of rewriting is enormous. Companies manage the debt by isolating risky parts, writing wrappers, and gradually replacing sections. They accept that the debt cannot be cleared all at once. They chip away where it matters most. Another example is mobile app development. Teams often rush to release apps with features that attract users. They may hard code values, skip testing, or duplicate code. These shortcuts allow them to move fast. But as the app grows, the debt slows every new feature. At some point, a team must decide whether to pause feature work to rebuild the foundations. If they wait too long, the app may collapse under bugs and crashes. If they act too early, they may waste effort on features users never wanted. Timing is everything. Even small projects illustrate the principle. A developer may write a script for personal use, cutting corners because only they will see it. Later, the script becomes popular in the company, and others rely on it. What was once harmless debt becomes dangerous. The code must be cleaned and documented. The developer learns that debt is not just about their own needs, but about how code evolves in unexpected ways. Technical debt is not shameful. It is a natural part of software development. Every decision involves trade-offs, and some form of debt is always the result. The skill lies in making those trade-offs consciously, understanding the costs and revisiting them when the balance shifts. Sometimes you borrow speed at the cost of cleanliness. Sometimes you slow down to pay back debt and secure the future. Both are valid. What matters is the judgment to know which path to take at the right time. The metaphor of debt reminds us that code has a future, not just a present. Shortcuts made today do not vanish tomorrow. They leave traces that must be managed. Pretending you can avoid debt is naive. Accepting it and learning to manage it is what makes a developer effective. The art of software is not in chasing perfection but in balancing progress with stability, speed with sustainability, and shortcuts with long-term health. When you sit down to write code, it may feel like a solitary act. The screen shows only you, your editor, and your thoughts turning into lines of logic. You may even call the project solo because you are the only one writing code for it. But the truth is, you never code alone. Every line you write depends on an enormous stack of work created by others. The libraries you import, the operating system that runs your code, the compiler or interpreter that translates it, and the developer communities that provide guidance all shape your project. Even when no one else touches your repository, countless people are involved in making your code possible. Take a simple Hello World program. At first glance, it is just a few words on the screen. But to display those words, the program depends on the language runtime, which depends on system calls provided by the operating system, which depends on device drivers that talk to the hardware. Each of those layers was written by someone else. Behind your one-line program lies millions of lines of code maintained by thousands of developers over decades. The illusion of coding alone fades when you recognize how much invisible work supports even the simplest output. Open source libraries make the connection even clearer. Suppose you are building a web app in Python. You might import Flask for routing, Sequel, Alchemy for database access, and requests for HTTP calls. Each of these libraries is the result of years of work by teams of developers. They provide abstractions that save you from reinventing sockets, parsing protocols, or managing connections. You may not know their authors personally, but their work is embedded in your project. When you run your app, you run their code too. Your solo project is already a collaboration. Operating systems are another silent partner. Whether you use Linux, Windows, or macOS, the OS provides memory management, process scheduling, networking, and file systems. Without it, your program could not even access the keyboard or display text. The operating system itself is a monument of collaboration, with contributions from thousands of developers. Linux alone has had contributions from more than 15,000 people over its history. When you write code on top of it, you are building on that collective effort. Even when you avoid external libraries and write everything from scratch, you rely on compilers, interpreters, and toolchains. A C program, depends on GCC or Clang to translate code into machine instructions. A Java program depends on the JVM to run. A JavaScript program depends on engines like V8 or SpiderMonkey. These tools are massive projects, each with its own teams, history, and bugs. The act of coding in a high-level language is only possible because others created the layers below it. The developer community also ensures that you never code alone. Online forums, Q&A sites, documentation, and blog posts are part of the ecosystem that supports you. When you search for an error message and find a solution on Stack Overflow, you are receiving help from someone who encountered the same bug. When you read a tutorial to learn a new framework, you are guided by another developer's experience. Even if you never post or reply, the community shapes your learning. The shared knowledge of developers worldwide becomes part of your solo work. Collaboration extends into the future as well. The code you write may be read, reused, or modified by others. Even private scripts often end up shared when colleagues ask for them. Open source projects often begin as personal experiments before growing into community efforts. The moment someone else reads your code, it becomes a shared space. Writing with clarity, documenting your intent, and structuring your work for others is part of acknowledging that you are not alone. The dependencies you rely on show another dimension of this truth. Every time you run npm install, pip install, or import a library, you pull in work from developers around the world. Some of these libraries are maintained by large organizations, others by individuals in their spare time. Your code inherits their choices, their bugs, and their style. When one of them updates a dependency, your project changes with it. Even without direct contact, you are linked to their work. The community of maintainers becomes part of your project, for better or worse. Security vulnerabilities highlight how connected coding really is. When a library you use has a flaw, your project inherits it. The infamous Heartbleed bug in OpenSSL affected millions of systems because so many projects depended on the same library. Developers who had never touched the OpenSSL code still had to respond to the vulnerability. They were part of a network they may not have even noticed before. Coding is never isolated, because risk and responsibility are shared across dependencies. Hardware also plays a role. Your code runs on processors, designed by engineers, using instruction sets shaped by decades of research. It stores data on disks built by other specialists and travels across networks maintained by infrastructure teams. The physical world underpins your software. Even if you never think about it, you are working with the efforts of thousands of people who designed, built, and maintain the machines your code depends on. Even the culture of software reflects shared experience. Best practices, design patterns, and style guides are not invented in isolation. They are the result of lessons learned across projects and organizations. When you follow a pattern like MVC, or use a design like RESTful APIs, you are drawing on a collective history. Your project may be unique, but the ideas within it come from a community of practice. There are also moments when the dependence becomes visible in unexpected ways. A single maintainer abandoning a widely used package can disrupt thousands of projects. In 2016, a developer unpublished a small npm package called LeftPad. The package was only a few lines of code, but it was a dependency for many projects. When it disappeared, builds around the world broke. Developers who had never heard of the package suddenly felt its absence. This event reminded everyone that even the simplest solo code can rest on fragile networks of shared work. Understanding that you never code alone changes the way you approach development. It encourages gratitude for the invisible work of others. It reinforces the importance of contributing back, whether through bug reports, documentation, or code. It also creates caution, because you know that your choices ripple outward. A library you publish may someday become a dependency for thousands. A bug you ignore may affect people you never meet. Coding is a collective act, even when it feels private. Even in small personal projects, this truth holds. A student writing their first program relies on compilers and editors built by others. A researcher writing scripts for analysis uses libraries maintained by communities. A hobbyist coding a game for fun depends on engines, APIs, and drivers. None of them code in isolation. The support of unseen collaborators surrounds every keystroke. The idea of coding alone is a comforting myth. It suggests independence and control, but the reality is richer and more connected. Every project is part of a vast web of shared knowledge, tools, and infrastructure. Whether you acknowledge it or not, others are always there in the code you use, the systems you depend on, and the lessons you learn. You never code alone because software itself is a collective creation, built layer upon layer by countless hands. When you first start programming, the compiler or interpreter feels like an obstacle. You write code, hit run, and are greeted with a wall of red text. The instinct is to see error messages as punishments, as if the machine is scolding you. But this view misses the real role of the compiler. It is not your enemy. The compiler is your friend. It does not exist to frustrate you, but to guide you. Its messages are clues, not judgments. Learning to read them deeply can teach you more than many tutorials, because they connect directly to the code you wrote and the mistakes you made. Take a beginner writing C code. They forget a semicolon at the end of a line. The compiler prints something like error expected before return. At first this looks cryptic, but the message is precise. The compiler is telling you where it got confused and what it expected. Once you learn to interpret this, you stop seeing it as noise and start seeing it as a map. The compiler is showing you the exact point where your mental model of the language diverged from its rules. That gap is where learning happens. Error messages are direct feedback loops. Tutorials show examples, but they cannot cover every mistake you might make. The compiler, on the other hand, reacts to your actual mistakes. If you misuse a type, it tells you. If you reference a variable that does not exist, it points it out. If you forget to handle a case, it warns you. Each message reflects the difference between what you meant and what the machine understood. Reading those differences carefully is how you grow from following examples to truly understanding. Consider type errors. In languages like Java or Rust, the compiler enforces strict type rules. Beginners often feel frustrated when the compiler refuses to accept their code, but each refusal is a lesson. If you try to assign a string to an integer variable, the compiler explains why that does not work. If you mix incompatible types in an operation, it shows you, over time you internalize these lessons, and your mental model of the language sharpens. What once felt like nagging becomes guidance. The compiler is teaching you the rules of the system in real time. Some compilers go further by suggesting fixes. Python, for example, often points out typos in variable names by asking, "Did you mean?" Rust's compiler is famous for offering detailed explanations and possible solutions. It does not just tell you that ownership rules are violated, but explains how to fix them. This is mentorship built into the tool itself. Instead of turning to a search engine, you can often resolve issues by reading carefully what the compiler tells you. The better you get at listening, the faster you progress. Warnings are another form of guidance. They do not stop the code from running, but they hint at potential issues. An unused variable may indicate forgotten logic. An unreachable branch may reveal a flaw in your conditions. Ignoring warnings is like ignoring a mentor pointing out weaknesses. They may not break your program today, but they highlight areas where bugs can appear tomorrow. Treating warnings with respect builds the habit of writing safer, cleaner code. Debugging also benefits from compiler feedback. When a program fails to build, you must trace the message back to the source. This process forces you to examine your assumptions. You thought the function had 3 arguments, but the compiler insists on 4. You thought the library provided a certain type, but the compiler says it does not match. Each error is a mirror showing you where your understanding is incomplete. Debugging with compiler messages is not just about fixing syntax, but about correcting your mental map of the system. Sometimes compiler messages feel overwhelming, especially in complex projects with many dependencies. A single mistake can trigger dozens of cascading errors. It is easy to panic at the flood of red text, but here too, the compiler is your friend. The trick is to focus on the first error. Often the later ones are side effects of the first. Fixing the root issue makes the rest disappear. This teaches you not only how to code, but how to approach problems systematically. The compiler rewards patience and methodical thinking. Experienced developers often praise languages with strong compilers because of the safety they provide. In Rust, for example, the borrow checker forces you to think about ownership and lifetimes. At first, this feels like a barrier, but once you learn to work with it, you realize it prevents entire classes of bugs. The compiler has become a partner in design, pushing you toward patterns that are safe and efficient. What felt restrictive turns into a form of collaboration. You learn to trust the compiler because it catches mistakes before they ever reach production. Even in dynamic languages, where interpreters run code without strict checks, error messages play the same role. A Python traceback may look intimidating, but it tells you the exact line and call stack where the error occurred. Reading it carefully saves hours of guessing. JavaScript errors about undefined variables or failed promises are not punishments, but precise signals of where your assumptions broke down. Whether in compiled or interpreted languages, the principle holds: error messages are tools for learning, not obstacles. There is also a psychological shift that happens when you embrace the compiler as a friend. Instead of dreading errors, you expect them. You see them as part of the process, not signs of failure. This mindset reduces frustration and builds resilience. Each time the compiler corrects you, you get better. Over time, you begin to write code that anticipates the compiler's expectations. You develop an intuition for what will pass and what will fail. The compiler's voice becomes internalized, shaping the way you think about code. Real-world projects show the value of this relationship. Large systems are too complex for any one developer to hold in their head. The compiler becomes an assistant that checks consistency across thousands of files. It ensures that interfaces match, that contracts are honored, and that dependencies align. Without it, teams would drown in errors. The compiler is the silent partner that keeps the system coherent. Trusting it and learning from its feedback is a survival skill in large-scale development. You can also see the difference between developers who read compiler messages carefully and those who skim or ignore them. Beginners often copy and paste error messages into search engines without trying to understand them. This solves the immediate problem, but slows long-term growth. Developers who take the time to parse the message, check the code, and reason about the cause build deeper knowledge. They need external help less often because they learn directly from the feedback loop. The compiler trains them to be self-sufficient. In many ways, the compiler is a more patient teacher than any human. It never tires of pointing out the same mistake. It never judges, it simply describes the problem and waits for you to fix it. Each message is consistent and repeatable. If you make the same mistake 100 times, it will correct you 100 times. Over time, that repetition builds mastery. Tutorials end, mentors move on, but the compiler is always there guiding your progress. By learning to see error messages not as punishments but as guidance, you unlock a new perspective on programming. The compiler becomes a partner in your work, not an adversary. Its feedback is often sharper than any tutorial because it responds to your actual code in your actual context. The better you learn to read its language, the more confident and capable you become. Far from being a barrier, the compiler is your closest ally in the long process of learning to code. Most people see progress in software as adding features, writing new code, and making systems bigger. But experienced developers know the opposite is often true. Progress can mean deleting code. Every line of code you keep is something that must be read, understood, tested, debugged, and maintained. Each line is a liability. Removing unnecessary logic makes the system lighter, easier to understand, and safer to change. Deleting code is not losing value. It is reducing risk and creating clarity. When you write code, it feels like building something tangible. You create classes, functions, and modules. The more you add, the more it feels like you are accomplishing. But all of that code carries a cost. It must be read by you and others, months or years later. It must be updated when requirements change. It may break when dependencies shift. If you write 10,000 lines to solve a problem that could be solved in 1,000, you have created 9,000 lines of potential bugs and future frustration. The system does not gain strength from size. It gains strength from simplicity. A common example comes from frameworks. Developers often generate boilerplate code, configuration files, or scaffolding. These files sit in the project for years, rarely touched, yet they expand the surface area of the code base. Every new developer who joins must wonder if those files matter. If they delete them, will the system break? Often the answer is no. The files add no value, yet they create cognitive load because they exist. Deleting them removes confusion and frees attention for what actually matters. Another example comes from feature creep. A product may accumulate small features over time, each added for a specific request. An extra filter here, a special option there. Each addition seems harmless, but the codebase grows. Eventually the team realizes that many of those features are unused or redundant. They clutter the interface and complicate the code. Removing them reduces not only lines of code, but also the mental burden of supporting features no one cares about. Progress comes not from expanding, but from pruning. Testing illustrates the same idea. Suppose you have a complex function with dozens of edge cases. Writing tests for all of them is difficult. But then you realize that many branches of logic are unnecessary. You can simplify the function to handle fewer cases more cleanly. By deleting code, you make testing easier. The number of scenarios to cover shrinks. Bugs become less likely. The quality of the system improves not because you tested more, but because there was less to test. Performance also benefits from deletion. Developers sometimes optimize by adding layers of caching, memoization, or special case handling. These layers may help in narrow situations but add complexity overall. Later profiling may show that the optimizations are not even needed. Removing them makes the system faster to maintain, and often performance is just as good. The most effective optimization is sometimes the removal of unnecessary work. A line of code that does not exist cannot slow the system down. Deleting code also reduces technical debt. Every hack or workaround you add to solve a short-term problem becomes debt that must be repaid later. Sometimes the best repayment is to rip out the old workaround once it is no longer needed. Teams that fail to do this accumulate cruft. Their systems become fragile and changes take longer. By removing code regularly, they keep debt under control. Each deletion is a payment toward long-term health. You can see this principle in the history of programming languages and libraries. Over time, projects often remove deprecated features, simplify APIs, or cut obscure options. This makes them easier to learn and use. Each removal is progress because it reduces the chances of misuse and focuses the project on its core purpose. Users may complain at first, but in the long run the ecosystem benefits from the reduction in complexity. Developers sometimes resist deletion because of sunk cost. They think, we worked hard on this feature, we can't just remove it. But effort spent in the past does not make bad code valuable. If the feature is unused, or if the logic is redundant, keeping it is not honoring past work, it is burdening the future. The discipline to delete code requires letting go of sunk costs and focusing on what actually serves the project today. One of the clearest examples is refactoring. You start with a complex block of logic, then gradually simplify it until entire sections vanish. The joy of refactoring often comes from deleting lines, not adding them. You realize that the same behavior can be achieved with half the code. What felt like progress before, more lines, was actually clutter. The real progress was understanding the problem well enough to solve it with less. Consider also debugging. Many bugs come from code that should not exist in the first place. Extra checks, unnecessary conditions, or outdated features create edge cases that break. When you delete that code, the bug disappears. The system becomes simpler and more reliable. The fix was not adding more patches, but removing the cause. Fewer moving parts mean fewer places for things to go wrong. In collaborative environments, every line of code you keep is also a communication to future developers. They must ask, why is this here? If the answer is unclear, they spend time investigating. Multiply that by a whole team over years, and the cost is enormous. By deleting code, you spare them that effort. You send a clear message: only what remains is necessary. The code base becomes a sharper tool for everyone. Even in small projects, deletion shows progress. A script that shrinks from 200 lines to 50 is easier to share, easier to debug, and easier to adapt. The reduction is not loss. It is refinement. Like editing prose, the best programs are not those with the most words but those with the fewest words that say exactly what is needed. Deleting code is editing for clarity. Large companies practice this at scale. Google, Facebook, and others run cleanup projects where they remove unused libraries, features, and code paths. These efforts free up build times, reduce security risks, and make systems more maintainable. The result is leaner, more robust infrastructure. The act of deletion is seen not as regression but as necessary upkeep. It is the digital equivalent of trimming branches from a tree so it grows healthier. Every developer eventually learns that the easiest code to maintain is the code that does not exist. Writing new code feels productive, but maintaining old code consumes far more time in the long run. Deleting unnecessary logic is an investment in the future. It reduces cost, increases clarity, and strengthens reliability. Progress in software is not only about adding. It is about subtracting wisely, removing what no longer serves the purpose, and leaving behind only what is essential. Every tool a developer uses promises help. A framework makes it faster to build, a library saves you from writing boilerplate, and a platform removes the need to manage hardware. These benefits are real, but they come with costs. Every tool is a double-edged sword. The same framework that saves time today may trap you tomorrow in its quirks, bugs, or assumptions. Each dependency is a trade, and the more you lean on it, the more you accept its limits. Understanding this balance is key to making sound technical choices. Take web frameworks as an example. When you use something like Django or Rails, you gain a huge boost in productivity. You can set up routing, database models, and templating in minutes. You avoid solving problems that thousands of others have already solved, but you also take on the framework's structure. Your application must conform to its patterns. If the framework's conventions clash with your needs, you spend more time fighting it than building. Later, when the framework updates or changes direction, you must adapt. What felt like freedom at first can become constraint. Libraries illustrate the same point. Importing a JSON parser or HTTP client is easier than writing your own, but each library comes with bugs, security issues, and design choices you inherit. If the maintainer abandons the project, you are stuck. If the API changes in a breaking way, you must rewrite your code. In some cases, a small library dependency pulls in dozens of other transitive dependencies. What began as a quick solution grows into a tangled web of risk. The edge that saves you time also cuts into your stability. Platforms like cloud services make the trade even sharper. Using AWS, Azure, or Google Cloud lets you scale without managing servers. You gain elasticity, global reach, and a suite of tools ready to use, but you also accept vendor lock-in. The more you use proprietary services, the harder it becomes to migrate. Code written around one provider's storage or queue system does not move easily to another. The dependency saves money in the short term, but may cost far more in the long run if you want to switch. Many companies discover too late that they built not just on the cloud but into the cloud, making themselves captive. Even programming languages are double-edged. Choosing Rust, for example, gives you strong guarantees of memory safety and performance, but it also forces you to deal with steep learning curves and strict compiler rules. Choosing Python gives you speed of development and a vast ecosystem, but it costs you runtime performance. Each language is a tool with strengths and weaknesses. Your decision is always a trade between what you gain and what you give up. Consider user interface frameworks. Something like React or Angular speeds up development by providing structure, components, and a large community. But these frameworks evolve quickly. APIs deprecate, best practices shift, and what you wrote last year may not align with today's standards. Teams find themselves rewriting large parts of code to keep up. The advantage of a large ecosystem comes with the burden of constant change. The same sword that cuts time to market also cuts stability. Dependencies also create hidden obligations. When you rely on open source tools, you depend on maintainers who may work unpaid in their spare time. If they burn out, disappear, or introduce flaws, your project suffers. High-profile security incidents, like the Log4j vulnerability, show how fragile these dependencies can be. Millions of systems depended on a single library, and when it broke, the damage was global. The double edge here is stark. Libraries save effort, but concentrate risk. Even your development environment is a trade. An integrated development environment like Visual Studio or IntelliJ can boost productivity with code completion, refactoring tools, and debugging aids. But once you grow reliant on it, switching becomes difficult. If licensing costs rise or the vendor changes direction, you face disruption. A lighter editor may demand more manual effort, but avoids deep dependence. The choice is not about which is best, but about which trade you are willing to make. The double-edged nature of tools also appears in patterns of abstraction. An ORM, for example, lets you interact with databases through objects instead of writing SQL. This saves time and reduces boilerplate. But when you need a complex query, the ORM may become a barrier. You must either fight the abstraction or bypass it. The tool that simplified your life for common cases complicates it for advanced ones. You cannot escape the edge of the sword. You only choose where it cuts. Some teams learn this lesson through scaling. A startup may adopt a framework or database that works perfectly for hundreds of users, but when growth brings thousands or millions, the same tool becomes a bottleneck. What was a strength at small scale becomes a weakness at large scale. Replacing it is costly and painful. The shortcut taken in the beginning creates friction later, yet refusing the shortcut at the start might have delayed launch. The decision was always a trade, not a mistake. Even version control illustrates this point. Git gives distributed power, branching, and collaboration, but it also creates complexity, with commands that can confuse and mistakes that can cost hours of recovery. Centralized systems like Subversion are simpler but less flexible. The double edge is unavoidable. No tool is pure gain. Each offers advantages and imposes burdens. One way to manage the double edge is awareness. Developers who treat tools as magical solutions often suffer most from their downsides. Those who recognize the trade-offs make better decisions. They know that adopting a framework means committing to its ecosystem. They know that each dependency is a contract with another developer's code. They know that every gain in speed comes with some cost in flexibility, stability, or independence. Tools are not free. They shift the work rather than erase it. Sometimes the safest path is to limit dependencies. Writing small core pieces yourself may take longer, but gives you control. Other times, embracing dependencies makes sense because time to market matters more than long-term purity. The key is judgment, not avoidance. Pretending tools have no edge leads to disappointment. Accepting the edge lets you prepare for it. You can build systems that isolate risky dependencies, monitor for vulnerabilities, and plan for migration. Examples from industry highlight the stakes. Companies that built heavily on Flash for web applications gained rich interactivity years before HTML5 existed. But when Flash was discontinued, their investments vanished. Others built entire businesses on Facebook's platform APIs, only to suffer when the rules changed. These cases show how the second edge cuts reliance on a tool creates vulnerability when the tool fades or shifts. The lesson is not to avoid tools, but to use them with eyes open. Every developer carries scars from tools that promised ease and delivered pain. A framework that seemed elegant but became obsolete. A library that solved a problem but brought bugs. A platform that sped things up but trapped the team in contracts. These experiences teach caution. They show that progress in software is never free. The double edge is always there. The art is learning to wield the sword without cutting yourself too deeply. When most people think about programming, they imagine a conversation between humans and machines. You type code, the computer reads it, and the machine executes instructions. But the truth is, the machine does not care how you write. It will run anything that compiles or interprets. no matter how unreadable or messy it looks. The real audience for your code is not the machine but other humans. Programming is communication. Every variable name, every function, every comment is part of a conversation with the people who will maintain, debug, and extend your work. Even if you are the only developer on a project today, your future self is one of those people. Think about the difference between two function names. One is called doStuff, and the other is called calculate invoice total. Both may work, but only the second communicates meaning. When another developer reads it, they know what the function is supposed to do. The first name forces them to dig into the implementation. Machines run both equally well, but for humans the difference is enormous. The second version reduces friction, saves time, and lowers the chance of misunderstanding. Naming is not a trivial detail. It is language, and language is how humans communicate. Consider formatting and structure. You can write a program as one long block of code, with no indentation or consistent style. The machine will execute it, as long as syntax rules are satisfied. But when another developer opens the file, they face chaos. With proper indentation, spacing, and organization, the same program tells a clear story. Functions become paragraphs, loops become sentences, and code flows like prose. Readability is not about decoration, it is about conveying meaning. Code that reads well teaches the next developer how the system works. Comments show how much code is about communication. The most useful comments don't repeat what the code is already doing, but explain why it is being done. For example, if a line increases a counter by 1, writing a comment that simply says increase the counter adds nothing. Anyone reading the code can already see that. But if the comment explains that the counter is adjusted to account for the fact that the array begins at 0, it tells the reader the intent behind the change. That context is what helps another developer, or your future self, understand the reasoning instead of just the mechanics. The machine never reads that comment. A human does. The comment bridges the gap between logic and intention. It tells future maintainers what you were thinking, not just what you were doing. Programming as communication extends to design choices. Suppose you design an API, you could make it cryptic, with functions that require obscure parameters, or you could design it to reflect how humans think about the problem. The latter reduces mistakes and improves collaboration. Developers who use your API are not guessing at hidden rules. They see a clear contract. The machine will accept both versions, but only one respects the humans who depend on it. Debugging shows the importance of communication even more. When a bug appears, the person investigating must piece together the system's behavior. If the code is a tangle of unclear names, duplicated logic, and cryptic shortcuts, the investigation takes hours. If the code is structured clearly, with meaningful names and consistent patterns, the same bug may be solved in minutes. The bug itself is the same. What changes is how clearly the original author communicated through code. The difference is not in execution but in understanding. Think about your future self coming back to code you wrote 6 months ago. At the time it was fresh in your mind, but months later the details have faded. Now you are just another reader trying to make sense of it. If your code is clear, it feels like a friendly note from your past self. If it is messy, it feels like sabotage. Writing code with communication in mind is a form of respect for the humans, including yourself, who must work with it later. Even error handling is communication. A cryptic error message, like unexpected exception, leaves users and developers in the dark. A clear message like database connection failed, invalid credentials tells the story directly. The machine does not care what message is printed. It will log whatever you write, but humans rely on those messages to diagnose and respond. The clarity of the message determines how quickly the problem is solved. Again, the real audience is human. Collaboration magnifies this truth. On a team, code is not personal property. It is shared space. Every line you write is read by others during reviews, debugging, or feature development. If your code is sloppy, others pay the cost. They spend time deciphering instead of building. If your code is clear, the whole team moves faster. Programming in a team is not about proving cleverness. It is about creating shared understanding. Clever code that saves 3 lines today may cost hours tomorrow when no one understands it. Documentation reinforces this idea. Code can communicate through names and structure, but documentation adds another layer. A good README, design doc, or usage example reduces confusion and builds confidence. It tells the story around the code, why it exists, how to use it, and what to expect. The act of writing documentation is the act of communicating with humans who may never meet you but will depend on your work. Machines ignore it, but humans thrive on it. Open source projects provide strong evidence of programming as communication. Thousands of people around the world collaborate on the same code bases without ever speaking directly. They rely on clear code, consistent conventions, and detailed documentation to understand each other. The code is the medium of conversation. A pull request is not just an addition of logic. It is a proposal in a shared language. The success of open source proves that programming is less about machines and more about human communication at scale. Examples from industry also show this. Large companies like Google and Microsoft maintain code bases with millions of lines of code. No single person can understand the whole system. The only way teams can function is if code communicates clearly across boundaries. A developer in one part of the company must be able to read and extend code written years ago by someone else. Without communication through code, the entire structure collapses. The scale of modern software depends on programming as a human language. Programming as communication does not mean sacrificing efficiency. Clear code is often more efficient in the long run because it reduces mistakes and accelerates understanding. Performance optimizations matter, but only after the system is correct and maintainable. A fast system that no one can understand will fail when requirements change or bugs appear. A slower but clearer system can evolve. Communication through code ensures survival, while silence leads to fragility. At its core, programming is writing. Like any form of writing, it is about choosing words, structuring thoughts, and conveying meaning. The compiler or interpreter acts as a grammar checker, ensuring basic rules are followed. But the style, clarity, and intent are for human readers. Machines execute, humans maintain. Writing code without considering the human audience is like writing prose without considering the reader. It may be technically correct, but it fails in its purpose. When you program with communication in mind, you shift your perspective. You stop asking only will the machine run this, and start asking will another human understand this. That change improves everything. Naming, structure, documentation, error messages, and collaboration. Programming becomes not just an act of construction but an act of conversation. The machine may run anything, but the humans who follow you depend on clarity. Programmers often dream of building perfect systems. Clean architecture, elegant abstractions, and flawless test coverage sound like ideals worth chasing. But the reality of software development is different. Reality always wins. Deadlines arrive whether the code is ready or not. Requirements change halfway through a project. Budgets, team sizes, and business constraints set limits that no developer can escape. You may want to design the most elegant solution possible, but sometimes shipping a working, if imperfect, product matters more than pursuing perfection. Imagine a startup building its first product. The founders need a demo for investors in 2 weeks. The developers know they could design a clean system with modular components and thorough tests, but that would take months. Instead, they throw together a quick prototype. The code is messy, features are hard-coded, and edge cases are ignored. It is not elegant, but it works well enough to impress investors and keep the company alive. In this case, perfection would have meant failure. Shipping something fast, even flawed, was the winning move. Reality set the rules, not the developer's ideals. Even large, established companies face this truth. A bank may want to modernize its old systems, but doing so would take years of planning and billions of dollars. Meanwhile, regulations change, and customers demand new features. Instead of rebuilding from scratch, the bank layers new code on top of the old. It is not elegant, and it creates technical debt, but it allows the company to stay compliant and competitive. Reality does not wait for the clean rewrite. The messy patchwork is what keeps the business moving. Requirements are another place where reality intrudes. A team may begin with a clear specification, only to have stakeholders change their minds halfway through. Maybe customers respond differently than expected. maybe the market shifts. The team has already written code, but much of it no longer fits the new direction. They must pivot, reusing what they can and discarding the rest. Elegant design cannot save them from moving targets. Software is not written in a vacuum. It serves changing needs, and those needs rarely align with the neat plans made at the start. Deadlines exert pressure that shapes code. A government agency might need a system ready before tax season. A retailer might need a new website before holiday shopping. A game studio might need a release before a console launch. In each case, missing the deadline can mean lost revenue, angry customers, or public embarrassment. Under this pressure, developers make compromises. They cut corners, simplify features, and skip polish. The result is often messy, but it meets the date. Reality forces trade-offs, and teams accept them because the alternative is worse. Business constraints also drive choices. A company may have only a small team or a limited budget. Developers may know the best solution involves advanced architecture or expensive infrastructure, but those options are not available. Instead, they choose tools that fit within constraints, even if they are not ideal. A small team may stick with a monolithic codebase instead of microservices because they cannot maintain the overhead. A company may use cheaper hosting even if it means slower performance. These decisions reflect business reality, not technical preference. This does not mean elegance has no value. Clean design and solid engineering matter. They reduce long-term costs and make systems easier to evolve, but they are not always the deciding factors. When a company must choose between perfect code delivered late and good enough code delivered on time, it usually chooses the latter. The ability to adapt to real-world pressures is part of being an effective developer. Knowing when to compromise is as important as knowing how to write elegant code. Sometimes the conflict between elegance and reality shows up in the tension between developers and stakeholders. Developers argue for time to refactor or test, while managers push for features to meet deadlines. Both sides have valid points. Developers want to protect the system from collapsing under the weight of bad code. Managers want to protect the business from losing customers. The resolution is often imperfect. Some refactoring is postponed, some features are trimmed, and everyone accepts a degree of risk. The negotiation itself is shaped by reality. Even when developers achieve elegance, reality can undo it. A beautifully designed system may fail under unexpected scale. A perfectly documented API may become obsolete when the business pivots. A well-structured module may need to be thrown away when requirements change. Elegance cannot guarantee survival. Only alignment with real-world needs keeps systems alive. Developers who cling too tightly to purity may end up building art instead of tools. The ones who succeed balance ideals with pragmatism. There are countless examples of this balance. Social media platforms often release minimal features first, then expand based on user feedback. The early versions are clunky and incomplete, but they test assumptions and prove demand. Enterprise systems often start as prototypes that grow into production, carrying all the flaws of their early shortcuts. Even critical infrastructure like airline software or hospital systems runs on patched, imperfect code because replacing it would take too long and cost too much. These systems persist not because they are elegant, but because they meet real constraints. The idea that sometimes shipping beats perfection does not mean developers should ignore quality. It means quality must be defined in context. In some cases, quality means robustness and security above all else, such as in medical devices or aerospace systems. In other cases, quality means speed of delivery, such as in startups racing for survival. What counts as good enough shifts depending on the stakes. Developers must learn to read the situation and adapt their approach. Reality also reminds us that software is never finished. Even after release, bugs will appear, requirements will shift, and systems will evolve. Striving for perfection before release is chasing an illusion. It is better to release, learn, and improve. This iterative cycle reflects the real nature of software as a living product. Perfection is not a destination but a moving target, always reshaped by external forces. The phrase "reality always wins" is not a call to abandon standards. It is a reminder that software development exists within larger systems, business, markets, users, and time. Code is not judged in isolation but in how well it serves those systems. Sometimes that means accepting messy compromises. Sometimes that means pushing back for more time or resources. But it always means recognizing that no matter how elegant your vision, reality will have the final word.